Thank you for coming. Oh, there it is. My name is Andre St. Dennis. I co-instruct the ELM 4702 class. Partner Jeremy Cornwall is here as well. And we just appreciate you coming out to listen to these student presentations. Students have been working on these projects for a semester and a half, and they've come a long way. I hope you see some good stuff in what they show you today. Each group will present for a few minutes, and then they'll ask for questions, and then they'll take you over to their respective tables to give you a demonstration of what they're doing. So make sure you line up some questions in your head and be ready for that. Anytime you want, just go over and get some refreshments. We're going to start today with Liam and Jacob, and they're going to introduce our project.
Hello, everyone. I am Jacob.
And I'm Liam.
And this is our Drone Stability Lab Trainer project.
So what is a drone? A drone is a closed loop control system, meaning it constantly measures the control system of it. So it's constantly measuring what's happening and comparing it to the desired motion. So then it makes the correction. So it maintains stability by staying level in the air, correcting if it tilts, drifts, or is unbalanced. A drone controls angle, position, and speed by adjusting the motor's thrust to the side that it needs. So if one side is tilted, hold on, go back. I keep pressing the pause button. So if like one side, we're going to imagine that this is a laser pointer, is like this one needs to go up. So it's going to increase the thrust, and it's going to decrease the thrust on the side. The sensor on the right provides the feedback, and the IMU measures the orientation, the gyroscope measures the rotation, and the accelerometer measures the motion. I really like that. Cool. Forget that last sentence.
What is a control system? A control system is something that measures how a system is behaving, compares it to the desired value, and then makes corrections to keep it where it needs to be. For our trainer, the main output is the angle. The controller compares the actual angle to the target value. If there is an error, the control system adjusts the motor speeds so that the trainer moves back and forth towards the desired position. This happens continuously in real time, which makes it a closed-loop feedback system. Real-world examples of this include a car's cruise control, which increases or decreases the tachometer to make the car move faster or slower to the desired miles per hour. Another example of this is a thermostat, which maintains the temperature. Background. Before we started designing our system, we first looked at the existing drone trainer. The idea behind this trainer is to give students a platform to experience with drone control systems. But the current system is way too simple. It only has basic sensing and feedback, and it doesn't connect to MATLAB or Simulink for real-time control development. It only uses a single fan, which limits how much control behavior you can actually study and doesn't have a smooth enough liftoff. And finally, the system costs about $3,000, which makes expanding or modifying it pretty difficult for our budget.
So our client wishes. So the main goal of this design is to make a simple single-axis trainer, so that way we can capture all the core dynamics of a drone without, going too crazy and cutting off people's fingers. Because a drone by itself is quite unstable and hard to manage. So making this one axis makes it a lot easier for us to actually record stuff and see it. So instead of fully dealing with the flight complexity, we are focusing on only the one axis and using two different ways to sense the angle of that axis. Yeah. We also want to keep it low cost, so that way we, can make a whole bunch of these things and not, run the school out of budget.
Our solution was to create an updated trainer that demonstrates a control system in a simple way. We used a single axis instead of a full drone, which made it easier, safer, and easier to test and understand. We added multiple sensors to the trainer that can measure what is happening and use feedback instead of running just an open loop control system. A second fan was added to create thrust on both sides, making it act more like a drone in balancing itself. The STM32 ran the control system in Cube IDE, while MATLAB and Simulink were used to monitor the responses in real time. The diagram shows the basic loop, the desired angle, measured angle, error, motor direction and correction, and feedback,
So our system diagram, we're going to, let's see if I can. So we're going to start with this. May have read? So we're going to start with the start and stop command. This all happens on the computer. So we're going to code everything in our Cube IDE and send that to the STM. The STM then will send whatever data it needs to send to the motor drivers to make them actually turn, because you can't do that without telling it to do that. And it will then record whatever control system we're running off, either the encoder mode or the IMU mode, and it will take where it is. So it will start down here, and it will go, all right, we're at 60 degrees. We want to go to 0. So how do we get there? So it's going to do some math down in here in this control system on the STM, and it's going to correct it and then make this move. And then once it is moved, it will then send the data back out to the Simulink so we can actually see what's happening in the system. So subsystem 1 is the IMU. So what is an IMU? An inertial measurement unit is the MPU 6050 can record both the accelerometer and the gyroscope. We're only using the accelerometer for this part, but I have the option to have both the gyroscope as well. So the accelerometer measures the linear acceleration along the XYZ axes. This allows us to see determine the tilt of the crossbar relative to gravity. We have the gyroscope, which we're not going to use, but it allows you to measure the angular velocity about the same 3 axes, which would allow us to see how fast the system is moving. So if we wanted to expand our system in the future, we would be able to just put this in as well and use the gyroscope. So where are we actually using this MPU in the system? It goes right in between the 2 motors, so that way it gives us the closest point to the axis of rotation, which is right about here. When the crossbar begins to move, the accelerometer will see the change and will spit that data to the STM, which it requests, and then we will do the control system and allow it to see that it's at the wrong angle or it's at the correct angle, and then make the changes accordingly. So, how is the IMU actually talking to the STM? So, the IMU needs to get a wake up command first. So you send it a wake up command, and the IMU starts sending out data. The STM then will ask the IMU for that data. The data will send a 14-bit data packet from the registers, and we are not going to use this temp and the gyro stuff, but it will send all 7 of these components of the information. So the register, it will then read those registers, see what is happening, and then send it to the Simulink if it's required. If it's not sending it to the Simulink, it's actively doing the control system and it's looking at the data and doing the math. Yeah. It's gonna. Oh, that's you. Yeah. So this slide shows how the IMU is actually talking to the Simulink. So the Simulink can't just receive the data. It doesn't work like that. You can't just send it, oh, it's at 45 degrees. It doesn't work. You need to actually send it the entire packet of bits that we were receiving from the IMU or the encoder, depending on what we're using. Decode that in Simulink in this little MATLAB function that we're using that will then give us whatever our data is, and we can display it on this scope. This is the packet command that I'm sending to the STM. This is just for the IMU, not the encoder part. I didn't include that. So it's each. Well, I'm gonna go back. Yeah. So after this, we can just see our recorded live data.
This was my first subsystem. It was an encoder position control demo. The encoder measured the shaft position on the STM32, which then used that as feedback to control where the pointer moved. The system moved the pointer in 90-degree increments instead of letting the motor spin freely. If the pointer was moved by hand, the encoder detected the change and the controller moved it back to the target angle. Then the measured angle was sent to MATLAB and Simulink so that we could monitor the live position. The image below shows the physical demo, including the STM32, the motor driver, and the physical system I used. This is the encoder I used. Here is a diagram of it right here. And here's the pulses it sends out. So this is a quadrature encoder that was used in the trainer, meaning it has A and B pulse signals. The pulse signals are shifted by 90 degrees, which lets the STM32 determine direction. Those pulse signals this tells the controller whether the shaft is rotating clockwise or counterclockwise. The encoder mounts to the rotating shaft and tracks its position as it turns. The STM32 then reads the pulses using timer encoder mode so that you can count positions automatically. Then the count is converted into an angle. Since we used 8,192 counts per revolution, we found the angle by doing 360 degrees divided by 8,192, which was 0.0439 degrees per count. Then the code at the bottom shows the conversion we used to get it into an actual angle. So it was the encoder angle, which is the wrapped encoder counts multiplied by 360 degrees divided by the counts per revolution. And then in the Simulink system, this slide shows how the Simulink monitored the encoder angle in real time. The STM32 calculated the angle from the encoder counts, which was the physical position of the needle. The angle was then scaled by 100, so we could keep 2 decimal places to increase accuracy. And then the STM32 sent the value as a 16-bit integer, which split into 2 bytes over serial communication. Then Simulink received the 2 8-bit bytes, rebuilt the value, and then divided by 100 to recover the angle. The gauge on the right displayed the live value, and so as the needle moved, the gauge updated with it in real time, right here. And then this setup helped us verify that the encoder feedback and watch the position response in real time.
So, subsystem 2. We had to start subsystem 2 by actually building the mechanical frame, which you will see later on. Actually over there. I think it shows up later in this presentation. So we're going to start with the pivot point. Wow, this is really odd. This is the pivot point and where everything, or the pivot assembly, where everything really comes from. So this bottom part gets connected into a piece of 8020, and then there's a crossbar that this piece connects to. So this is the pivot point. This is the motor driver mount. This gets just placed right on top of the pivot point. The pivot point has 2 bearings in it, so that way the axis of rotation doesn't have a lot of friction in it. This is the IMU mount. It gets placed on the crossbar between the 2 motors. This is the motor mount. The motor gets placed right here on this, and then it gets slid onto the crossbar. This piece goes on right before this piece, so that way it covers the motor, so that way we don't chop our fingers off when we're trying to study this thing.
So this was my second subsystem, which was the encoder-based balance control system. The goal of this was to balance the drone trainer at a 0 set point where the beam was level. The encoder was used as a closed-loop sensor feedback so that the STM32 always knew the actual beam angle. The STM32 then compared the measure angle to the target and then calculated the error. A PI controller used KP and KI to decide how much correction was needed. KP fixes the correction, KP fixes the current error, and KI was to decide how much correction was needed. Then the correction was sent to the motors with pulse width changes, which adjusted the thrust on each side of the trainer. If the beam was tilted, the motors changed speeds to push it back toward level. The diagram below shows the physical control loop. What did I just do? It has the desired angle, the STM32 acting as the controller, the motor driver, motor, and frame as the weight on it, and then the feedback goes back to the measured angle, which goes back to the desired angle. Oh wait, that's me again. This slide shows the control code used for the encoder balance system. The first code calculated the angle error by comparing. This slide shows the control code used for the set point. The error then was integrated over a 10 millisecond loop so that the controller could account for the error that stayed over time. The integral error was limited to prevent the system from overcorrecting and teetering back and forth. KP and KI were continued to create the PI control output. That control output was converted into ESC pulse width changes, which then controlled the drone motor speeds. The tuning value shows the KP and KI settings used during testing to reduce bouncing. Then the lower code section shows the PI equation used to update the integral error and calculate the final control output, which is right here. The control output is KP multiplied by the single error angle error which is added by the Ki multiplied by the integral error. So these are the physical trainer attributes. So this is where the encoder was used. This shows the physical hardware for the encoder balance control system. Real drone components were added to the trainer to make it more realistic for drone control testing. The STM32 controlled the drone ESCs using pulse width signals, and the ESC controlled the brushless motors. The brushless motors used three-phase motors, and the propellers created the thrust to move and balance the trainer. The drone battery powered the motor side of the system so the drone parts could run properly. And then all these parts were mounted and wired onto Liam's physical drone system.
Cool. So my subsystem 2 was, of course, building the frame and then this IMU-based control system. It works very similar to Jacob's part, except the feedback is not an encoder, it's this NPU angle based on graph. It's not as exact. So it's not as exact. It's a little jumpy, but it's similar to how an actual drone works. Because they don't have an encoder on it. They have an accelerometer, gyro. This thing 45 degrees. 45 degrees this way, it's going to fly. We don't want it. So this is just a PI controller right now. I've been still working on the D part of it. And we'll move on. Next. So this is how it's actually being implemented in my code. I had to, don't mind the red lines underneath this. I had to take a snippet of it. So the PI control implementation for subsystem 2. The first step is to read the angle as we got. So the PI control implementation for subsystem 2 is here for the angle. The first step is to read the angle. So the IMU angle minus the target to give us the error. Used here for the angle. Down here, so we use the IMU angle minus the target to give us the error. And we use that gives us the control output. AP gain times error and AI to change times the interval IMU. That gives us our control output. So then send this given to the motor command, and then we send whatever our updated angle is after the control system happens. So then all this is used, and then we send whatever our updated angle is after the control system happens, because we don't want it will be choppy and it won't stabilize as well. So, yeah, mission responsibilities.
For my side of the project, I focused mostly on the encoder feedback, motor control, and software side of this trainer. The final part is the encoder-based PI control system. This used the encoder angles as the feedback, compared it to the target angle, and adjusted the motor output to correct the error. Together, we both focused on making sure the project was wired clean, has housing for the external parts, presentable, user-friendly, and make sure it was safe to not injure the people watching or the users of the project.
And my main focus was the hardware and the IMU control. And once I calibrated the IMU and was able to get an accurate, or a very close to accurate reading from it, I then started working on the actual Simulink monitoring part, which then once we got that done, I started working on the frame. And once we both got the frame and the motor control figured out, we both started working on the control system separately. We have our two different control systems. So here's our timeline where we start out with our calibration. Let's try to do it. You can see this timeline. It's what I stream at it.
It just shows the goals and standpoints of our timeline that we had. All right, so this is the budget side of it. This shows the overall production cost for our updated trainer. We have all of these parts. I'm not going to label each an individual part and how many we used for it, but overall, our lab trainer costs about $241, which the original lab trainer was $3,000. So our design created a lower cost and while still adding real sensors, drone components, and closed loop features.
Questions on the presentation before we walk over and demo it? Inertial measurement unit.
All right, so we're going to go over and show everyone our what we have done on here.
This one is actually really nice. It does return to
Here's the
zero
startup.
after I release.
And as you can see, it's a relative zero. It has a couple degrees of error, but it will eventually just balance itself out.
Pretty hard.
The control, or the encoder
Anyway,
one.
that's all we're
Mine,
going
the
to.
encoder.
Working as soon as I would show this, so.
And yeah,
Control system is actually working by listening to this motor right here. So when I tilt this down, it's going to speed this motor way up. It's trying to correct, but it can't. And then we go past it, we're going to hear this one try to speed up. It doesn't sound the same because it's a whole complex thing of this. This drone controller does not work very well, and it's very hard to work with. So this is
yeah. So the motor driver is what really just controls the pulse widths of the actual trainer, but then it comes in a set stack. And the set stack actually has a flight controller on it, and the flight controller is what controls like the actual speeds and adjustments. And you can't actually like the way we needed to use it, we needed to make it a control system, so we couldn't use the flight controller. So we had the flight controller try to control it in a specific way. And for some reason, it only works with a helicopter mode. So you have your back rudder, which is the slower one, which is the one on our right, your left, and then the main propeller, which is the one on this side. And that's why that side runs faster than the other side. And that's why we also have a counterweight.
yeah.
And that's the I part of the control system. You get the step.
We're still working.
our next step.
We're still working.
We have 2 weeks.
Yeah.
That's what we have left.
Whoop, I unplugged it.
This is true for all projects. Their final demo is during our final click, so a little ways out. So this is towards the end, but not the actual end. But you essentially be working on these projects.
I was trying to get it to work last night, and then it didn't work, and it made everything not work. So I reset it and went, this is good enough to show.
Yeah.
So,
We needed something to show you.
but I can see if I can try
Yeah.
to get the.
So does anybody have any questions for Jacob and Leah?
It looks like you attached a weight to one side instead of me.
Yeah.
Having it fall to not being balanced.
Yes.
Because if we.
Yeah.
It's off. It,
Very well,
Yeah.
harder.
It's
it balances. It tries to go this side, but it's easier with this weight on it. So.
Do you wanna show the IMU part?
Yeah.
The IMU part isn't as accurate as the encoder part because the IMU is what's actually on a drone. And if you watch a drone fly, it kind of oscillates back and forth a few times. The encoder is an actual position because it takes the counts and makes it into an angle. So it's way more accurate, but you can't use an encoder on an actual drone. So
Also, I've been having a lot of problems with this accelerometer for the past 3 days, and I have no idea why it started doing this. It was working perfectly fine and sending out all the data I needed to do my conversion to angle, and now it is not sending out my AY and my AZ value sometimes. It just decides that it doesn't want to work. And then I press reset, and everything works flawlessly. So let's see if it will actually function.
Right, still electrical. I'm not mechanical.
it's doing it again.
Let's see if we look at the live expressions. Oh, no, it's actually. Oh, there it is. See, it's going to balance a lot. It's harder for this to balance because when it corrects over the 0 point of this accelerometer is perfectly level. So if it goes past that at all, it has no idea really how to correct it. I've tried a bunch of different things, and this is the best I've got it so far. I'm still working on it. I had it working, it was pretty balanced, and then I added more weight to it, and it changed the entire system. So this one loves to bounce back and forth.
And that's the I part of the control system.
The ability to have both of these motors working properly and full speed, I assume it would balance a little bit.
That is our next step. We still have
Look at that.
Yeah, so we have time.
Yeah, their final demo, this is true for all the projects. Their final demo is during our final click, so a little ways out.
last night,
Working, it was literally working.
and then it didn't work, and I made everything not work, so I reset it and went, this is good enough to show. Yeah, so we needed something to show you. I can see if I can try to get the.
So does anybody have any questions for Jacob and Liam?
It looks like you attached a weight to one side just to
Yeah.
have it default to not being balanced.
Yes.
Yeah.
Yeah.
It's off.
Make it a little harder.
It balances. It tries to go this side, but it's easier with this weight on it. So, do you wanna show the IMU part? I can try to get the IMU part to work. The IMU part isn't as accurate as the encoder part because the IMU is what's actually on the drone. And if you watch it,
Should be able to use a whole bunch of different sensors on this and do a whole bunch of labs with this trainer.
Some of the things we brainstormed was adding some kind of thrust sensors. Exactly how much thrust we really putting out.
If you remember
Those
from
are
the slides,
A lot. Those are pretty expensive too, though. That was also a problem. They're like $200 just for a little thrust sensor.
So
Those are things we never do in a field trial. Quite
in
right, but go to a lab, set up.
in our original like diagram of this, we have a tachometer on it. If you remember from the diagram, we don't use that at all on this, but it was planned to have one.
Also really expensive.
Very,
some
very
reason.
expensive for no reason at all.
There was something the client told us that you have to look at your bucket, realize it's actually completely unnecessary.
Yeah, we did build a PI-based control system without a tachometer, so we didn't think it was necessary for now, at least.
Yeah, just
What led to the high cost of the original?
I'm not sure. It's just like it's one of those.
should add zero.
Yeah,
Pistol.
yeah. It's a commercial drone trainer.
It is this
That is the actual picture
This
of it.
thing is in
Yeah.
our lab, and they bought like a whole bunch of them. They got a grant for it. I was told that this was like $500, and then like 2 presentations in, I was told it was $3,000. And it was like,
Yeah, our client wasn't very honest with us on how much it was. So that's why also we didn't add many sensors to it. Because we were still trying to keep it super cheap, and we thought it was $500. Then we were told it was $3,000. So yeah, it did change the.
I've tried a bunch of different things, and this is the best I've got so far. I'm still working on it. I had it working with 3,000, and then I added more weight to it, and it changed the entire. So this one loves to bounce back.
There was a flame coming out of the top of it.
If we have the ability to have both of these controllers working properly full speed, I assume it actually does. This
Point out, and you saw it in the last presentation, these students are required to worry about the mechanical design. Actually, the last two students weren't required to think about the mechanical design, yet they had to do it anyway. They're not electromechanicals, but most of the students here are electromechanicals. So they're required to look at the mechanical design issues, the electrical issues, the mechanical design issues, and software. So I hope you'll notice that as these students present. There's a lot of stuff they're talking about, and it covers 3 major technologies. So I will turn this over to Richard. He's going to tell you about his trainer.
Can you guys, I'm thinking about not using the microphone. Can you guys in the back hear me all right? Okay. So I'm Richard Page, and this is my thermal process trainer. So what is a control system? So a control system is a mechanism that regulates the behavior of a device to achieve a certain outcome. So a good example of that is cruise control in your car. So if you're traveling down a road and you enter like a hill, if you were just driving, you're going to end up wanting to like ramp down in speed because the forces going up is going to block your car. So you put cruise control on, and it then makes your car ramp up to the certain RPMs that you need to be at the constant speed that you want. So that's kind of like the same idea with my hair dryer here. The hair dryer is a open loop system, so that means that any of the systems or any of the controls on it are switches that the human would press. In my system, it's a closed loop system. That means it has a feedback signal to regulate all of the modes. So if I want to regulate the temperature or the flow of the system, it's all by feedbacks within my system. And it also decreases, the whole point of it is to decrease the error of the system. So why don't we just buy one? Usually around a VTC control systems class for Jose is around 12 to 14 students. And each one of these costs around $1,000. That'd roughly be around $14,000 rough. And the professor wants it to be able to have certain modes or certain monitoring that this processor here would not have. Such as it doesn't have any MATLAB, which the professor really likes to use to simulate graphs and everything. And then here we go. What does the professor want? The MATLAB to make live interfaces. He wants to be able to have more thermal systems instead of just rotational or translational mechanical systems. And he would like to use these to create PID controllers to regulate the system. So so the problem statement for this is that senior students entering Controls 2 lack the access to use a physical thermal process turner to allow real-time adjustment of the fan speed and temperature through MATLAB. This project would then increase the ability for students to learn hands-on control PID tuning and see how systems work in real time. So my solution, I have an airflow system, a heater system, and a digital system. These are all part of one huge system. And I have these color-coded lines for the next slide. And basically, we have actuators and feedbacks. And the actuators will induce the reaction, and the feedback will take the reaction and then tell it to either increase or decrease based off the PID. So this is my system overview. So we have our fan here. This fan has a PWM. This PWM has a frequency, and that we need to control that frequency or the duty cycle. And it's set on my microcontroller. As that air goes through, it's going to push the heat through this heater, through the tube, and it's going to record the temperature of the air on these thermocouples. And this mass airflow sensor here will then take the flow rate that it's pushing at and, take the flow rate, and these two things, the mass airflow sensor and the thermocouples, are the feedback. So these two go back to the microcontroller and then tell the fan or the heater if they should increase or decrease. And then we have CubeID, which is just the software where I code, and then we have MATLAB, which will be monitoring all that data. And we have here, our fan here is also going to have a fan and tachometer, and the tachometer is one of the feedbacks for our Cascade PI controller. So this is kind of what my MATLAB interface is going to look like. We have 4 graphs. We have our fan speed, which will increase based or decrease, or based off the system I have it on, will show you exactly how the speed's reacting based off my PIDs. And we have the flow as well. That will be, the flow will also be like directly correlated with this fan speed. So in some cases, in the RPM mode, it will not, because the RPMs will just stay constant at whatever RPM you set it to. And then in the cascade mode, this will then follow this flow right here. And then we have the heater temperature, and then the heater duty cycle. And the duty cycle is the PWM cycle that will be affecting the heater coil for that. So this is our physical. So this is the physical model. This is just the prototype. The full piece will be made out of aluminum. But I'm presenting my plastic version, the prototype, because everything works within the system. So I designed this entire system on SolidWorks, and then I 3D printed it out of PETG. I printed out of PETG because it has a higher steady point and a higher melting point than regular PLA or other 3D printed plastics. And it's within all the tolerances or the heat that the system will come to. So here is where the heater is going to be, and then the fans right there. All that heat and air is going to be pushing through this. These are the thermocouples that will be taking in the heat and then bringing it to the microcontroller. And this is the housing for the mass airflow sensor, which will also be sending data to the microcontroller. This is something that I made fairly recently. It's a iris mechanism for the throttle. So part of the system, because we're teaching students about errors, this right here will induce an error by blocking the fan's ability to bring air into the system. At the end of this process trainer, the mass airflow sensor, as it's fully closed, will read 0 and want to ramp this fan basically up to compensate. So this is just a mechanism that I use to simulate that error. So this is the heater control system. So if you remember back to here, we have our thermocouples that introduce a feedback. And that feedback will then tell us if we need to bring the KP up, the KI up, or the KD up. We have our equations here. I've already come up with values that work pretty well, but when students are using this, they're going to end up doing all the equations themselves and then trying to find the proper PID for the system. The main part about this process trainer that's very difficult and what students need to learn from it is that this system, it takes for the air to get to this end, and the amount of time it takes for the air to heat up and get to equilibrium takes a transport lag. It has a certain amount of time from one end to the other. And with those 3 thermocouples on the graph, you can actually see the time in between it takes. And that's what we call transport lag, which is simulated right here in the graph as a time delay. Also, this plant here will be the physical model of this system. So all the feedbacks and the sensors will be into this plant as a physical model. So here's some of the code that I made for my PID. We start here. This is the error of the system. So it's the set point minus the temperature control. That is what essentially comes back and through the feedback and then gets added to the controller. We then have our integral and our derivative. And then we have everything as one formula here. So this Ki here is the gain of the system times the error. Oop, sorry. And then we have the heater Ki times the heater integral. And then that's basically this Ki times the integral, or times the integrator. And then we have the heater Kd times the temp derivative, and that's that section down there. So this is some of the simulation graphs that I had picked up during my experiments with it. So this system right here I don't know why it's not doing the laser. Yeah, so the graph on the left is a system that I first started using when I was just putting in the original KPI, which is proportional integral derivatives, into the system. And I did not tune it yet. This was just my first draft of it. And you can tell that there's a little bit of ups and downs, and that basically means that the PID is not tuned, or it's not in its most optimized orientation. So the system in that graph is not stable. The system on the right side is stable because it comes to a point when it regulates and it does not have any jumps or divots. And you can see that the heater duty cycle starts at 100, so it ramps all the way up, and then as it gets to the set point, it starts to decrease. That decrease will get to a certain point, and then the heater will turn back on, and then it will come back up, and it will start oscillating until it gets to a perfect equilibrium, or try to balance within the set point. So this is the airflow system. I ended up using a Cascade PI controller for this. A Cascade PI controller is basically a control system that has an inner and outer loop. So there's two plants and there are two controllers within the system. This helps with getting rid of a lot of disturbance, and it's called a dual disturbance rejection model. So basically we have our outer loop equations and inner loop equations, and then those get put together into one huge controller. So this is my airflow software. So we have our PI loop for the RPMs and the PI loop for the flow. Because these are two separate systems, I can have two modes. I can have one that uses the outer loop as a set point, or I can use the RPMs as a set point. If I use the flow as the set point, I then use the tachometer to follow the flow to make sure that the RPMs are staying consistent with the set point of the outer loop. So basically I can, if I want a mass airflow of 0.011 per se, my RPMs will then follow that to make sure that the set point stays consistent. And then the other mode, RPM mode, will just have the RPMs stay at a speed controller, so you can set it to any RPM you want. So this is some simulations that I had made for the airflow system. So in this right here, in this orientation, it is the cascade. So we start the system up. It wants to ramp up to the set point, and you can see that it's oscillating and following the disturbance or the turbulence within the pipe, because it wants to shoot up and come down and shoot up. In this orientation, the PI is not exactly tuned perfectly, but we wouldn't be able to get a straight line anyways because of the turbulence within the pipe. So with this system, it's right now, it's not perfectly tuned, but it's right there. So this is my wiring schematic. We have thermocouples and amplifiers. We have our fans and our mass airflow sensors, our heater, our market controller, and our thermocouples here. I'm just gonna isolate these thermocouples real quick. We have thermocouples, and these thermocouples go to the amplifier. So these thermocouples cause they produce really small voltages, so we need amplifiers to amp the voltages up so the microcontroller can actually read it. So that's like a cool factoid about that. And yeah. For this project, I had made a website, and I don't know why that's cut off. Yeah, it just says website. I don't know why it's cut off. For this project, we didn't need to make a website, but I wanted to make one because I had never made one before. So all it has is theory and math and drawings and simulations, sensors I used, pictures and videos that I had made for the whole semester. This is my Gantt chart. So throughout the whole process, all the weeks, I was doing research on mostly control systems and the math behind them. And then we had a tech topic. We had our first subsystem, our second subsystem, and we had personal goals that we wanted to achieve at certain dates. Yeah. So this product, like I said before, was around $1,000, and some of them range. It goes from like $1,000 to $1,500. With all the budget that I had used and with all the money that I had used, it came up to a total of $205. So basically dropped the amount by 5 times. So it's pretty efficient. Yeah, sorry. Kevin is going to end up making enough for all the labs and then using them for the students. So they're going to be all made of aluminum. Is that your question? Yeah. No. The 3D printed rolls, the PETG that I had used were around $40, and then one of those pipes for one is around $20, and then I had bought legs, so it's about $40 for each. Yep. Any questions? Like to introduce an error. Yeah, so the throttle that I had used for the airflow system will then block the airflow into the system. So, yeah, yep. Yep. And then for the heater system, to introduce an error, we were thinking about buying some type of coolant, or not coolant, but like some type of way of cooling the front of the inlet so that the heater can then ramp up or ramp down depending on how cold or how hot the system is. Yeah. Yep. Yep. Well, the systems work independently. So you can either have the heater on and then have either one of the modes for the airflow, or you could just do the airflow mode without the heater. You could, I set it up like this so that Jose has freedom over how he wants to do the experiments. Oh yeah, they work together right now. You can either have them, the heating system and the airflow system working simultaneously, or you can work them independently. No, yeah, I have an interrupt. So whenever the system feels an error, it will then interrupt and then change the error. Yep. And they run off different timers, so technically they could work simultaneously. Yep. Yeah. Yes. So the way that we've been doing controls too with Jose is that we've been given a script. We've given some of the MATLAB stuff to moderate. I was going to give Jose my code and then my MATLAB, and then have him either change and set the PIDs to 0 and the PIs to 0, and then have the students do all the math behind it. Or just let him do whatever he wants with it. But in my opinion, I would just set the PIDs to 0 and then have them do all the math, because that's really what the class is for. Yeah. Any questions? Any more questions? I guess this is the part where we do our demo now. So if we follow me over here. Okay, so now it's bouncing out. You can tell that it's bouncing out. Oh, I forgot. I don't have, so usually when I'm testing this, I have a laser tachometer, and it's an external device I can point at the fan. It'll tell me how fast it's rotating. I had forgot to bring it. But these numbers on these screens right here, if you see where my mouse is, are pretty accurate.
You're going to have to read into
Sorry?
read the
Can you like make this just bigger,
Can I make it
Richard?
bigger?
Like just globally? Just like
Oh,
the font, I mean?
I
Like just
don't-
Control Plus or anything like that?
No, it won't work.
Yeah, I
Won't
was gonna
work?
say, I think
It
it's
does?
just, it's mimicking the pixels on my laptop.
Yeah.
Okay, so the
Just
system,
read to them what's happening.
yep, the system is working now. So now I'm gonna start my MATLAB, and it's gonna start.
Jeremy, can you just read the RPM? Just say the RPM, what it's doing.
It's starting up right now. Like I said, my computer's been really slow. Here we go. So we see fan speed right here. We are running at 1300 RPMs, and now I'm going to plug my fan in, or my heater in.
Yeah, it is ready. Yeah, low flow.
So now we can see that the heater's starting to get like go up in temperature. And this is the other thing with this fan, or with this heater, is that this heater has a really slow startup time, and it stays at 100% of the duty cycle until it gets to the set point. But it takes a very long time for the heat to actually get up to the desired temperature. And then we have the fan blowing on it, which is going to cool the fan down, or cool the heater down as well.
So you can see the heater duty cycle's at 100 up the top here.
Yep.
And then we have the mass airflow off his mass airflow sensor is being read off in the middle. And then we're seeing the temperatures start to climb. This is off the 3 thermocouples that he's got in the bottom of it.
So
So
this blue line on the left side that you guys are seeing is the closest to the heater. So that one's going to feel the most amount of heat. The third one at the very end of the mouth is the yellow line, and that yellow line is controlling the entire system. So once that yellow line or the mouth gets to 70 degrees, it will then start to control itself and balance.
So eventually the heater duty cycle will start to drop once the temperature's up to where it's supposed to be.
You're welcome to come up here. It's not super hot, but it's clearly warm.
How does the mass flow sensor work? What kind of sensor is that? Is it measuring mass flow or airspeed?
It's a mass airflow sensor. It's this guy right here.
Yeah, it's a Nissan mass airflow sensor, and it runs voltages to the micro, but it does measure, basically it does volumetric flow and it does the mass flow, but in this system, the mass flow wouldn't change, but the flow rate would change. So we use the mass airflows for the multi-purpose.
So the sensor accounts for the density changes when it heats up.
Yes.
It's got all that built in.
Yeah, based on my calculations.
Yeah, mass airflow sensors are used in any even remotely modern internal combustion car.
Yeah. We stole
Which is
this
why
from
we use
somebody's
the Nissan.
Nissan.
So we can now see that the heater duty cycle is starting to decrease. And that's because the yellow line has now reached 70 degrees Celsius. And as it starts to regulate, you're going to see that duty cycle is going to come up and down until it starts to get really narrow. And that narrowness is how it balances itself. It just goes back and forth and regulates the error.
So in that way, it's similar to what you saw with the drone, where the drone was oscillating around the final endpoint. And this eventually gets there, but it's temperature that we measure.
Yep. And because this is a heater, like I said, the system is very slow. So you'll see this, I've been doing a lot of testing on this, you'll see it bounce around 400 seconds. And that's when it starts to be completely
Yeah, delay makes it really hard to design a control system that would quickly damp out any oscillations. So it's not going to work quite as well as your cruise controller, what you have on an elevator going to 410, what have you.
And a good example is the first one you saw that was back and forth had a really big eye unit, so that eye was oscillating a lot. And when I was doing my testing for the first subsystem demo I did just a pure P controller, and that pure P controller balanced it out at like 600 seconds or 800 seconds. It was around there. So the PID actually does make it compact and steady. It gets to the steady point faster. And that's because your I is ramping the system up, and then the D is then a lead compensator. So, but those two put together, it's really balancing the system as optimized as possible, or as optimized as possible.
So Kevin was recording the fact that the heater was working. There's a coil heater in here that's getting red hot, and you can see it if you look down the end of the tube. So you can see real heat coming.
And it does take a while, so I can let it sit, or I can just change it to cascade. Change it.
Well,
so,
yeah. Go ahead.
So now it's in RPM mode, and now if I change it to cascade mode, which is one of these buttons here, this one is RPM, this one's cascade. I'm going to change it to cascade. On here, it then will change. You'll see it changes to mode cascade, and then we can see that the airflow or the air speed will start to increase because we now have a set point for the flow, and then that's going to try to oscillate and regulate the airflow instead of just having a constant RPM.
So how would a student walk up, like same question as this one, how would they come up, what would they do when they're using this trainer? When
Like from start to finish?
From start to finish. Students
So,
learning about control systems, what would they do when they come up?
So in the class, Jose will do half of the semester before doing a project. So I don't know, 8 weeks. So they have a good understanding what a PID is. What they would get is this system or that system there, and it'd be on front of their desk. It would have all the sensors already. They would have to find what the gains of these sensors are, the gains of the actuators, put them together mathematically, and then with our equations that we do in class, you then find out what the P and the I and the D would be. So
So when you
it would
say
take a good amount of time.
when you
But
say
they're trying to control a temperature or something?
Yeah,
Or the airflow.
or the
both.
airflow. I made it very generalized so Jose could do whatever he wanted with this system, because I'm just making the product for them to use in the class.
when you said they have to find the gains, those are like 1 week experiments, right?
Yes, yes.
They have to set up an experiment and plot what the heater is doing as a function of time.
A good example of that is this fan here. To actually find the transfer function for it, I used Picoscope to find what the time constant of the fan was. Instead of taking it apart and figuring out every mechanical inertia, I just did a test and it gave me the time constant. So they would do that same test. And I'm going to have it all written on a user's manual for Jose. But it's the same thing with this heater. I had set the heater up and I timed it from 0 to the end of the heating, so as high as the temperature get, and I took the time constant of that as well and put that in my my transfer function for the heater unit, or for the heating system. So the teacher or the students would be doing the exact same thing. Yep.
There was a question asked earlier about which takes the lead, the heat or the flow. That's neither, as he answered, but one thing that we have noticed is the heater and the fan both saturate pretty quickly. So there's a fairly small range of flow control, and there's a small range of heat control. So part of the reason for the,
so the cascade is moving the RPMs of the fan up and down?
Yes.
Yeah.
But the heater is also turning on and off, or is that?
Yes, we run it at, we run it at 6 hertz. And
this right here, Andrew, if you come up, this is the duty cycle on the heater. So you can see it's going up and down in relation to the temperature that's being read out. And so like when it was too cold, it was running at the 100% to try and ramp it. And then the temperature started to get up there, and so it dropped the duty cycle. And so it's also, it's oscillating quite a bit, but eventually does damp out.
They're doing them together.
It's doing them together.
And even with the most optimized.
And so you can see right here, this one's the RPM for the fan. And so you can see these are all running in real time, I mean, as we speak. And they're working around to get to whatever target point he set for each one. And you can change those independently. Right.
And now, actually, this is a good spot to see this. I'm going to show you the flow here. So this is one of the experiments the kids would do. I would then take my throttle and I would close it, right? Now the airflow is going to go down. And we can see that on here. And then what that's going to do is then this airflow is going to want to ramp all the way up to compensate for that error. So
can you show the airflow on the...
right there.
Scroll down. So you can see right there, it's where you close the iris. And so the airflow went all the way down. And so it's going to try, within its limited scope of, this is just not a super powerful fan, it's going to try to overcome it. It's not really going to succeed, but it's going to try.
And I put a cap. This fan is only good for 2200 RPMs. And with the cascade system, you can set whatever set point you want. I just put 0.011, which is the most amount of airflow that this is going to come out with, this fan. So you can see that it's ramping all the way up, but it's not ramping all the way because there's a cap on the amount of RPMs that can come up.
Have you considered a more powerful fan for the final
I
version
have.
Kevin's going to make a bunch of?
I have, and actually that's what this is for. So on this metal tube, on the cold end, there's no hot air that's going to affect any of the plastic. So you can 3D print any part on the non-heater side. So this is a part that's just a press-in, and you can take it out or put it in, and you can change basically your square to have whatever fan you want. So I ended up making a file where Kevin can just come in, and whenever fan we end up coming up with, he can just change the box diameter, and that fan will mount right to the end. And the same with the parts for the iris. It's the same thing. You can just change the square for whatever you want.
Essentially, you've done some parametric CAD design, so you can just change a number and switch out the fan. It doesn't have to be remodeled from CAD from scratch.
Yep. But I ended up using this fan because it was really convenient, and it has a really cool feature. It has 4 pins. It has a power, a ground, a control, and a tachometer. So it has a tachometer built into it. So it's really nice for that RPM feedback.
Anybody have any questions?
And you can also...
Oh, John, you got one.
I was just going to say, are you inspired by poorly written instructions from professors and to write a really good manual that's crystal clear to the future, future students?
Very crystal clear. And actually, if you look at the graph now, if you look at the temperature, since it's been closed, it's actually staying at 100% duty cycle, but the heat is now decreasing because the airflow is not cooling it down. So basically, these aren't feeling any of the heat anymore because there's no airflow. If I were to open it up, then the airflow is going to push the hot air towards the sensors.
Scroll down so you can see the airflow.
Yep, now it's starting to come back up.
You can see right there, that's where you reopen it, so the airflow spikes back up.
Yep. If you had a more powerful fan, you could put your hand over it or something, and more air would want to come through, and you can actually feel it. When this one you can feel it too, it's just not as powerful. So you can't, it's very minuscule to feeling. But you can see it very well on this graph.
Remember, some of the design constraints are we need to use parts that are easily obtainable and you know, the overall cost matters, and so within those constraints is pretty good.
Yeah, a $200 fan would not be reasonable for this
Yeah.
system. So the fact that I bought this fan for $20 was very like affordable.
The other thing about this system, he's got 3 temperature sensors. If he was designing this for a real commercial installation, there'd only be one. You'd only care about it in one place. But by having multiple sensors, it allows for the instructor to change up the experiment and you know, come up with interesting things for the students to do. And it's a similar concept to the drone, where you know, the students executed that with 2 different angle sensors, and they might add a 3rd one. So that's what makes this a trainer. This is not a commercial product, but
in my presentation, I talked about a transport lag, and you can actually measure that transport lag in seconds by taking when each one of these hits 70, and that would be the amount of time it takes for each one to get to equilibrium with the set point. Yeah, so that would be your, like, really what you're looking for, because you would want to decrease the amount of time it takes for that transfer lag, and usually that's just by increasing the amount of flow and increasing the heat of the system. Because if you have more heat and more air, then it can get to the position faster. But we also can do that with a PID as well.
So you could set this up to do a delta T. You could feed gas in and do a delta T control, or you're trying to control it so you're getting a delta T across 2 sensors?
Yes, that's actually the main thing that Jose wanted this whole system for, because when he was getting his master's, I think, in control system, he had this exact system, but it was like really old. So he just wanted a new one that wasn't expensive. And that was actually the one on the screen was the one that he ended up using. But again, $1,500 times, or $1,000 times 14 students, $14,000 for just trainers. Kind of ridiculous.
I think Jose wants your instruction manual written in Spanish as well.
I guess I'll have to learn Spanish then.
That's what ChatGPT's good for.
You don't know.
Yep. Do you guys have any questions? Anybody?
All these things will be around later, so if you think of something while we're in intermission or something, come back and ask them. And you're welcome to come up and, you know, put your hand in front of it, show yourself as really working, that kind of thing. You won't get hurt. This is all pretty low temperature stuff. But otherwise, thank you so much, Richard. Next screen is set up. Come on down. So I just want to make a point. Richard mentioned Jose several times, and Jose Lizardo is one of our instructors. He can't be here today, but he will watch these videos. And he was the client in this case. So one thing we did in the last 2 years is move to client-based project design. In the past, sometimes the students would come up with a project. I want to build a robot. I want to build this or whatever. Now we have industry people or our other instructors or people from other departments pitch ideas to us, and so that's a common theme now that you'll see in all these projects. The students don't get to choose how well they work; they have to make it work to a certain spec. And so this group is going to talk about a snow groomer, and the client for that is Kevin, the guy who's recording there, because he wants to use it on the VTC ski hill.
Good afternoon. I'm Amelia. This is Keith Carrera and Luke Williams. Our senior project is as Professor Santana said, an automated snow groomer for the VTC ski hill. So some background on the ski hill. Right around 1939, the ski hill was established, and then over time, a rope tow was installed and then later upgraded as it had became old. It operates under only natural snow conditions. There is no SO generation on the ski hill. It is open to the VTSU Randolph community. And in recent years, an initiative started to add an automated snow groomer to the ski hill. Starting with last year, there was an associate's capstone for mechanical to build a prototype chassis, a proof of concept chassis, which you can see in the bottom right. That it shows it pulling 300 pounds of water jet garnet as a test simulating if it was to be tilling the snow. And our project here is developing the automation system, which sits on top of that proof of concept chassis which we'll explain more as we continue talking.
So just a background of snow grooming. Most of us are Vermonters. We all ski, snowboard, so we've seen them a few times. The steps of snow grooming, it usually starts with tilling. You're surfacing, shaping, redistributing the snow around, and then they usually compact it, and then they set up the trails after they're done, pushing snow around. So we have human responsibilities. The first one is driving the machine around. And then they usually level it out and they plow where the depth is over 2 inches. And we are going to focus on driving the machine around, but not a human doing it. It's going to be all remote controlled.
Which leaves us with our problem statement, which is to design and implement an automated control system for handling the drive, navigation, and safety systems, as well as making sure that it is expandable in the future so that additional senior projects in future years can add more onto this, such as that tiller and plow that was mentioned. We have some requirements listed on there in terms of how they replace humans in this application. One is having some self and situational awareness, which is sensor equipment. We have operation modes, one of them being the manual mode, which is remote controlled, which you'll see later, and one of them being automatic, which you may also see later depending on the weather. We also have to consider safety with both mechanisms for machine and technician safety for when the vehicle is being worked on, and bystander protection for when it is actually in operation. We also have to consider, of course, it has to be weatherproof and expandable.
So this is our solution. That is the groomer right there. So like Amelia said, we have to have some sort of situational awareness. So we start off by having sensors all around the groomer so it doesn't run into anything. We're going to have an RC mode so you can drive around with the controller, or it's going to be fully autonomous. It uses GPS to get its navigation path, and it has to have self-monitoring capabilities so we can see what the battery voltage is at, how much current it's pulling, just, the things to double check and make sure nothing is going wrong. So this is our system diagram of what the autonomous mode would look like. So we have the groomer down here in the bottom left. It's going to have some indicator lights. It has the GPS navigation system that talks to a satellite. And this little red line is our grooming path. So that will be made in the navigation system. So the groomer will drive along, and if there's a log in the way, the log doesn't have any thermal capabilities, so it'll see that and say, okay, that's just an object, we can drive around it. So then it will then create an obstacle avoidance path, and then it'll get back on its navigation path, and it'll keep on grooming. So then we have down in the bottom right, we have a human. And then this is when the thermal sensors come in, and it'll see that and say, okay, there is something that is living, breathing, and moving in front of us. We're not going to move at all. We wait until that gets out of the way, and then we just continue on our grooming path. So this is our block diagram of how all of the electrical stuff is working together. So we start off with the remote control, and that will talk to an RC receiver, and then on the main controller there's a switch to control whether we're in automated or RC mode. So if we're in RC mode, the RC remote will talk directly to the receiver, send the motor commands, and then the motor commands get turned into RPMs, which then get sent to the motor drivers, and then it'll drive. If we're in the navigation mode, the switch will be turned on here, and then it'll start pulling angle data from the navigation from where our desired path is, which then gets pulled in, turns into motor controls, sent to the motors, and then it drives the tracks.
So of course, a very important portion of this automated system is that navigation. The ideal solution that we are working towards here, as you can see in this image on the right, is a system where you can input bounds of a rectangular area on a map, and the navigation system will automatically generate a series of alternating lines within that, which it will then follow. Of course, it's important here to remember that the difference between this and certain other automated vehicles is that this is not driving from point A to point B. You can get from one corner of a box to another, but in that process, you have not necessarily groomed the ski hill. So rather than transporting the vehicle between points, we need to create these vectors to follow. We are going to fit this nicely into one of those control systems you've heard so much about today. As you can see here, we have a bit of a diagram. This is not a one-to-one representation of any physical objects, but it is a representation of how this works mathematically. In blue, you can see all of these boxes happen in the navigation system, and in orange, all of these boxes happen in the drive control system, which is Luke's wheelhouse. We are going to start with that pre-programmed path information I mentioned in the previous slide. From that, the navigation system is going to measure its location as well as its bearing, and it's going to create an error signal to send to that drive system to adjust the direction of travel so that we follow a path.
And then I am going to take that information I get from the navigation system, and then I turn that into drivable signals. So I take this angle and a indicator that pretty much tells me that we have to go forward, and I turn the tracks on to 450 RPMs, and they will spin at that speed the whole time. And then when the angle comes into play, it starts putting the differential mix into the tracks, so then it can start turning left or right or however direction you want to go. So this is just a little block diagram I made of my driving system. We've been talking about it a ton, so it's not hard to understand, but we have the input between auto or manual mode. It gets sent to our STM32, and then that will start pulling from the navigation system, and it'll get sent to these flip sky motor controllers, which then control the motors that have encoders on them that feed back that speed, so then they can stay at a specific RPM. It's all controlled by a PID control system, so then when you start going up a hill, it'll ramp up the current. It'll start going that speed the whole time, no matter if you're going uphill, downhill, or it's all flat. So this is my current autonomous drive code that I'm using. So as we've been talking about, we have our drivable line right here, and then we're going to have our heading angle right here. So that's how far we are off from the position that we're going to. And so up here, like I was talking about, you get a drive status from the navigation system that is going to send our tracks to 450 RPMs. And then we calculate our offset if an angle is put into play. So if this was 0, this is 0, the offset is 0. It's no longer being added or subtracted from our base RPM, so the left and right RPMs are going the same speed now. But let's say we do have an angle. Let's say we're at like 10 degrees. We have a steering sensitivity that's a multiplier, so that would be our gain in this situation. And then that gets multiplied by the angle we're getting in, and then it's either added or subtracted, since we're in a range from negative 100 or negative 359 to positive 359 we can receive from the navigation system. And then that will get differentialed right here. So if it's a negative, this becomes positive, this side would become negative. This is going, you know, less than this side. It's pretty simple math, and it actually works kind of well. But since there is no control system to this part, you get really close to your driving path. And then since it's just all proportional, you have no eye to go and dampen those oscillations. So you're driving up this path, and then it'll just go back and forth and back and forth. So we are going to improve that with the next part of the system.
Perfect. Yes, so like Luke said, we have tested the system shown on the previous slide and proved it not to be adequate. Instead, and to note, importantly, depending on how this is implemented, it's actually, you can either consider it a proportional controller or an integral-only controller. Either way, it does exhibit those oscillations that Luke mentioned. Rather than that, we are going to implement a PI controller, or again, in this case, depending on how you implement it, it can be either a PI or a PD controller. The method I'm going to be using makes it a PI controller. Using this, we're gonna use the system described on the right side, which is actually inspired by how certain aircraft navigation systems work, specifically a VOR receiver in certain light aircraft. And what this does is it uses the proportional signal mentioned on the previous slide, being the D there. How does this work? So that D there is the normal distance at a 90-degree angle from the target vector that we are trying to follow to the snow groomer. This is actually an analog of what was shown on the previous slide, because it is calculated through that angle to the reference point. In addition to that, though, we need to know how fast we are traveling away to or away from that line. And using the bearing provided by the GPS receiver in this system, we can simply subtract that from the intended path, get an angle error, and be able to control the system much more precisely and with less oscillation. So I'm going to give you an important preface here, which is that I'm a student in the Williston section of this course, so I'm going to be presenting next Monday up in Williston on a far more detailed explanation of how this system actually works. Today I'm only going over what it does in the context of this groomer. So what's going on here is we are using a solution that relies upon GPS, which you may know from your phone does not really provide more than 4 to 5 meters of accuracy at best. As it turns out, there are solutions to this. There's something called RTK, real-time kinematic correction. And this claims to provide up to 1.5 centimeter accuracy for your GPS receivers. Crazy, I know. I haven't seen that yet, but I've gotten pretty close. And the way this works is that you have your GPS receiver on your vehicle and a GPS base station located at a fixed point. In this case, it's probably going to be at the top of the ski hill. The base station, being fixed, can use a steady known GPS signal to generate a correction, which is then sent over a radio or internet link to the vehicle, which uses that correction to adjust its own position solution to a much more accurate and precise coordinate plot. Like I said, I have over here the PI control system again. At a constant speed, we know that we control the heading, which corresponds to the actual steering of the groomer, which is our proportional element, and then the normal distance from the track is actually the integral term because it's how far away you are from this path, built up by that steering. Keith.
So, on safety, there's a few important areas. One, we talked about making sure that the bystanders are aware that this is existing, making sure the bystanders are safe. So we do this through lights and through guards. The guards also doubling as safety for anyone working on the snow groomer. If anything was to start moving, it would keep them safe. Additionally, if there's electrical failure, the motors are not going to be able to stop the snow groomer, and so we need to have some sort of emergency brake which activates upon loss of electricity. So for bystander and user protection, we talked about the safety lights. We can see the safety light is indicated on the picture, and that will make sure that even over cresting a hill, any bystander, usually skiing or snowboarding, would be able to see the vehicle. Anytime this vehicle is running, these lights would be on. This includes the headlights, which will always be on while it's running. The emergency brake at this time, there's been a lot of discussion about how to implement it, but there's been no actual start towards implementing it. And then for the mechanical guards, we are looking at implementing a mechanical guard over the chain, which is circled in blue on the bottom left picture on this slide. For obstacle detection, we are looking at using multiple zones with ultrasonics and infrared. And using the ultrasonics, we are detecting the obstacles. And then with infrared, we're determining whether or not those obstacles are humans or some other living being, like a dog or whatever that was with you while you're skiing, or just someone hiking around with snowshoes or something in the middle of winter. Throughout the testing of this, we have not found infrared sensors that have been suitable for this purpose. We are still doing research to try to find infrared sensors. So at this time, we have only gotten ultrasonics to work for this purpose, and more research will be done to find whether infrared will still continue being the best route or whether some other route will have to be used to detect humans. The main reason being that infrared sensors tend to be susceptible to vibration, and with the snow groomer constantly vibrating, that causes issues for the infrared sensors, which usually leads to false positives that need to be verified through another sensor. which in this particular case, the ultrasonic sensors struggle to verify the infrared sensors because the clothing that we are wearing tends to absorb the sound instead of reflecting it back to the sensor. As the ultrasonic sensors work off of sending out a sound signal and then waiting to hear it back, and then using the speed of sound, figuring out how far away it is. Now, on system monitoring, to find out what the status of our system is, we are mostly doing temperature and thermals, using the temperature of an inside to make sure that it's not too hot. If it's too hot, we can identify there's probably something going wrong. It should be fairly unlikely, but if in case there's electrical fire and the system doesn't shut down immediately, the temperature sensor should be able to identify that something like that is occurring and we need to shut down the system. Additionally, for the current, we need to have an idea of how much charge the battery has. So that way, if we are running low on battery, we can return back to base instead of being stuck on the hill if we die. How this works is it integrates the current over time during charging and discharging to have an estimate of where the charge is currently. And on the charging side of things, if it is charged for a certain amount of time, it will, or charge a certain amount of current, it will assume that it's at full charge. Usually this will be like 110% of the rated capacity, 105 or 110% of the rated capacity of the battery. That way we never hit a point where we're just continuously going and we end up with an incredibly large number of a large amount of amp hours that we're just never going to run out from, and then end up dying because we have run into that situation. So this diagram may not be super readable at this distance and size. This is the current circuit diagram that we are implementing right now. We can see the 5 ultrasonics for the 5 zones that are connected in the microcontroller, each one over UART. And we have a current sensor, a Hall effect current sensor, which is in series with the main drive and primary system load. And then we have our internal temperature sensor, which is hooked up. And that is a thermocouple, which was used. It was a very quick decision made because thermocouples are linear. And that was pretty much the only factor that goes into it, because I was just making the decision quickly. But as a result of that, because thermocouples, how they work is they create a very small voltage difference. That voltage difference has to be amplified to then read into the microcontroller. And so there's a thermocouple amplifier that is attached to the thermocouple before sending the data, in this case actually over SPI, another communication protocol, to the microcontroller.
So we've just talked about autonomous. Now we're going to talk about the fun stuff, the RC remote. You can drive it around yourself. So pretty much we use this Frisky Tarnus X7. It's just a normal drone remote. Like you have your normal inputs. It's got a bunch of extra switches on it. But that sends signals over to our drone controller here. And it's taking those normal RC inputs of PWM pulses, and then it's going to output them here as either throttle, steering, or a limit pulse. And then I'm taking those and then I'm deciphering them down in the STM, because our motor controllers don't use the PWM to drive the motors. We're using the electronic RPM. So this is just some of the code that I've been doing all this with. So I take those PWM pulses that are coming from the drone controller, and then I normalize them down to -1 to +1. So then you can think about it as like a percentage. You're putting 50% of the throttle into the actual forward motion of the motors. So that is what I am doing up here in the top right. And then I'm going to multiply those by the RC limit that is on the left side of the controller. And that is also normalized. I just don't, oh wait, I did put it in there. That also gets normalized from a percentage, so that just gets multiplied by the amount of pulses that you're putting in. So after we go and set the limit on our throttle and steering, we're gonna go and do the same differential driving that we did for the autonomous mode, actually. So if a steering pulse gets put in, it's going to subtract the either like 0.7, 0.8, whatever you have. It'll turn this positive, the left side's going faster, and the right side becomes negative, the right side's going slower. And then I'm going to turn those into the electronic RPM using the max RPM of the motors. So if I didn't do that, then I would just be sending a percentage still, and these motor controllers take in the electronic RPM, like I said, when you're using the UART. So I multiply our max RC RPM, and then I multiply our left power and our right power, which are still in percentages, and then that gets us an actual RPM that we're going to send to the motors. So this is our division of responsibility slide. Amelia has been working on the navigation, all of that. I've been working on the RC mode, some of the safety stuff like the lights and the indicators, the autonomous driving, like I said, the indicators, the motors. And then Keith is working on some of the sensors, temperature, current, battery voltage, and then the guards and the emergency brake.
Now, for our timeline, start out by doing research on what even is this problem that we have that we need to solve, looking into different ways to solve it, coming up with our initial plan to solve that, and then we began working on getting our initial systems working with compass and acceleration before that ended up stopped being used in favor of using other stuff with GPS, getting the operational microcontroller set up, and then start getting the sensors online. And with a lot of these cases, what we started finding was the problem was more complicated than we were initially expecting, such as for the sensors, there's how many different ways there is to measure current and other problems, as well as whether we should be measuring current. Initially, we were looking at using voltage measurement for the batteries before concluding that it wouldn't work very well for finding out how much charge there is on the batteries, so started moving to integrating the current, initially doing that through a shunt resistor, and then moving to Hall effect sensors. And so these individual problems started fairly small, and then over time, as we started doing more research on them, we found them to take a little bit more time than we were expecting. Alongside this, we learned a lot of stuff with like obstacle detection, as well as with a lot of stuff with the operational drive system. We ended up having to Luke ended up having to switch out the motor controllers because the initial ones we were using were not well suited for this application. And so there's a lot of areas in here where we were working on it in the beginning, and they ended up running a lot longer than expected because the problems ended up becoming a lot bigger than we initially were planning on them to be.
This is our budget. As you can see, it's a lot of money. This is certainly one of the more expensive projects done here. Again, I won't go over each item line by line, but we've spent about $3,400 in total on this.
Notice how the big ticket items are the motor, the main drive system, and the batteries for it, alongside the navigation equipment. Pretty much everything else is fairly cheap on it, relatively at least. But the drive system and the navigation system are two very big ticket items on the budget. Any questions? A lot of stuff got stretched out and finished very recently.
There's a few lines there that are going past this week. What can you just talk about that very quickly?
Yep. Those are items that are either nearly done or in that closing process where there's tuning that we need to do. A lot of it related to integration with making stuff work with the rest of the equipment, or as far as I'm aware, the RTK is it's in the progress of being finished. It's gotten working, correct? It's been proven, but it has more tuning to get it to the operational status that we would like it to be.
Yeah, so most of the development, the unfortunate part is that it's cold outside and it's hard to receive GPS signals indoors. So I have mostly been working inside buildings to develop this. In that process, I have been able to confirm that all the RTK stuff works. I'm still just finalizing PCB design, some enclosure work for an RTK base station to actually put outside permanently. But I have been able to see down to about 0.4 meters of accuracy inside a building on the Williston campus.
Any other questions? I got to drive it around a little bit, not in autonomous mode. It actually drove really well in the snow. So, yeah, I have a ton of videos of it crashing into stuff and, you know, all the good stuff. There's a video of me pulling my car with it. So, yeah, it's got some power. It's pretty cool.
Crew has just taken it to a whole new level with the autonomy, the safety, self-navigation, all of that. But the actual, what was built upon was our second year students last year.
So over here, we're first going to show you the obstacle detection system. Right now it's not mounted on the snow groomer, but we have it over here to show you. We have three out of the 5 ultrasonic sensors working right now. I'll show you that, and then we'll show. Correct. This is running all the time. Our microcontroller has 2 cores, and so one of the cores is running all this sensor processing, and then over shared memory, it is sending that information to the second core that's making the operational decisions. And so all the information on this screen is actually being sent over. What time the information was collected, a bit mask of the zones. Unfortunately, I can't show the individual bits here, so it's the integer representation. But there's a bit mask showing which zones are detecting something. In this case, these sensors, when they aren't detecting anything, they just read 0. So anytime that they're not reading 0, their respective bit on this bit mask is flagged, and then Luke can just go, is this bit mask 0? If so, he doesn't have to do anything with it. If any of the sensors are seeing anything, it will not be 0, and then he has to start looking more into what is actually going on with this information. Yep. The IR, the plan is to have it be fairly similar, where they each cover these zones, and then have a very similar zone processing, so there would be a second set of data for, basically this data would be duplicated for the IR and the IR values, and if they have any extra information they can have, as well as at that point then coming to some conclusions, fusing the ultrasonic and IR data together and coming to conclusions of we need to stop immediately, and and other conclusions that might be able to be used by Luke's system. Yep. Those are a separate. So this is in one data structure. For those of you who know C programming, there's a separate data structure that's not being displayed here, that is looking at looking at the current of the system and the temperature, the internal temperature of the system, and those are being transmitted the same exact way. They're just not being shown on this screen right here. I actually have the code commented out right now to not show it, so you can focus on the obstacle detection right now. Currently, the spec is from -50 to +50 amps, if I remember correctly. That will be changed in this next week by increasing the Hall effect sensor to 5-volt supply, and then running the output through an op amp to decrease the 5 volts into the range that the microcontroller can use, which is 3.3 volts. And that will make it so it's negative 60 to positive 130 volts. Or not amps, not volts, amps. And that should cover all the situations from charging all the way up to the current spikes on the motor starting. Yep. The reason for that change was the Hall effect sensor doesn't have to worry about the Hall effect sensor doesn't have the saturation, or it doesn't have to, when it hits the saturation, you don't blow anything up. It just continues at its max, which helps keeps all the parts safe. And usually, theoretically, the Hall effect sensor should not be maxed out, which means that even though we now can have the safety of if we reach that max, nothing happens, it shouldn't reach that max, so it shouldn't affect, and if it does, it will be very brief, and so it shouldn't affect our integral very much. Additionally, getting all the other parts working with the shunt resistor, using a differential amplifier, and all the sensitivity related to that, it was just easier to go with a Hall effect sensor that was able to be directly in series with the rest of it and not affecting any of the other factor was the voltage drop across the shunt resistor, trying to make sure that we're not affecting the voltage of the rest of the system.
Since we're inside a building right now, a bunch of zeros. We should go outside and do Luke's system first.
Limit pins. Yeah, it's all pretty straightforward. This is the lights. The lights aren't on anything in here. It's all just off on this switching relay right here. So we have that going on, front lights, and switch it on and off. This will be controlled by an LDR, so when it gets dark outside, it'll see that, and then this will just go and control it. Just replace the switch. Super simple. But now I'll drive it down there, and then whoever wants to drive it, you can. I'm gonna go down this way, so just so you guys know. I put the RPMs down a lot, but if you go left with this one, it'll start to turn left. You gotta hold it, so the PID in it has to see that it's not moving, and then it has to ramp it up to the side. If you hold it to the left, it'll start to see if you hold the current, it's working. All right, well, who else wants to drive it? So it takes a second to see that it's not moving.
So we want to thank you, gentlemen, from Gary for coming. I'm Jeremy Cornwall, I'm a professor, and also for
But it has pretty decent control until you start getting it up like really hot. But
one of my colleagues,
and I have the RPMs down.
and he told me that we're in a air position, we're supposed to be position. You guys only would have
Yes, there's a slot.
It's evolved over time. So I just wanted to see,
All right, who else wants to drive it?
It's not really what we could do.
It seems that going reverse for the motors is different than going forward. So you send the reverse command. You see that this side will go forward, but this one won't. There's a little bit of like push. Yeah, it's really interesting. I haven't figured out why it does that yet, actually, but
depending on who's doing.
They're pretty hot.
But I mean, we're just running out. These wires too. These are small gauge wires. If you feel them, they're a little toasty. Yeah, those are actually fun. Like it's just.
You wanna explain the parts of it?
To the stream.
Could do with a.
All right, stream. So this is a battery pack for the drone controller, and the drone controller will then send PWM signals to this motor control board. I can actually pull it out. So the motor control board is just a surface mount to the microcontroller, and it plugs straight into the headers. And in the code, I'm turning those PWM signals in a -1 to 1, so it's pretty much a percentage. So 1 is 100%, -1 is -100%, so it's just reverse. But I'm turning those into that value, and then I'm converting that percentage into the electrical RPMs that then get sent over to this motor controller, and then that ends up driving these with the PID control system. That is the feedback right here to the motor controllers. You gonna plug it in?
Do you want to?
Yeah, let me pull it out.
Do you want to explain the parts of your system? Yes, let me install it first. I should also we found earlier that this vibrates a lot more than you think, and sometimes it makes pins.
Yeah, we disconnected it.
Hence the fact that I've
He made the drums He made a from scratch. Yeah, try hard. Keep in mind, sure. Yes, so what I was saying is, sometimes these positions, you don't always do a good job of rating the opening and stuff that's posted on white. Somebody had in mind something they were looking for, but like differential when we hire engineers, we can. Like
yeah,
maybe they're like more specific,
particular.
Or like
we thought about that, but
maybe
just
this,
this
but that doesn't mean that like we can't put somebody that's really good or something.
Maybe have a switch so you can switch it between.
Yeah, so the problem is, like, you see how this...
Yeah, it does have the spring back. I had the same issue with that. I got this.
Yeah, we definitely...
Kevin had one and he just rotated. Or maybe it was Mike, I don't remember. Somebody just rotated it, so then you still have this...
Yeah. Okay. So, I'm going to give a preliminary test of the GPS system here, the automated GPS system. What it's going to do is I've selected actually just on Google Maps a point which I believe is like just a few feet out from that tree, and a heading of true north to follow. So in an ideal world, if this works right now, and I can tell you that it still needs some PID tuning, we can place this groomer somewhere down this way, start it up in automated mode, and it will drive to that path and start following it up until it reaches this point, at which point it will stop. I have found a few things that might create issues here. Number one is vibration. There were a few times we were testing this where the vibrations from the groomer disconnected wires on here. Number two is actually, even though the location that I am receiving from the GPS is accurate to 0.55 meters right now, there are different standards. There are different geological surveys that provide different offset locations on the Earth. And I can't confirm which one Google Maps uses, and I believe that it is actually like 10 meters off from what a GPS will tell you.
It depends.
So I need to go find a different app that I can use to confirm that I know what geological survey it's using and be able to connect that to this. So it also, I believe the actual point, even though I selected on Google Maps to be over there, is actually kind of closer to where we are right now.
Oh, okay. Yeah.
But I can talk to, Diana, Kelly, and HR.
Anyway, Luke, if you want to drive it over this way.
Whoever judged no, maybe. I don't know how to drive it. I don't know. Yeah. Yeah, send me an email and I'll.
Yeah, I saw you guys on Todd Taylor around. I couldn't get it.
Oh no, my laptop's
Uh-oh. Thank you for
Yeah, so I do hope to come up also with.
Actually, I might be able to plug it in. You want to grab the black battery pack that's sitting on
When
my
he came
stuff?
out last year.
This is actually my final semester. So I took a break from studying.
Yeah, we want to either at the sophomore or senior level, and that could be mechanical, electrical, electromechanical, any of it. And it could be something you genuinely want. Most of our countries, sometimes they actually really want this. How it goes. Right. Like, hey, let's see what these kids can do. They really want it. Yep. So it could be something real, or if you kind of want to see what these kids can do, we welcome those projects too.
Yeah, the reason I didn't jump on it is when you guys initially were soliciting is that, like, well, the real problems we have are mostly defensive. So just like it would be a lot of projects to make that work. But yeah, if something comes around and like it's directly project related, like wait, like we've got the time to kind of make this go through 2 semesters. It's not a
Quickly.
part thing, or if there's like quality life.
Can you just plug it in that type C cable?
It's charging this.
Oh, that's not what we want. Discharge it.
These kinds of problems I had to solve for this application.
Oh, that's good. It's on. Slow charger. That's good.
You've got 2 bars.
See if I can go closer.
I I clicked it and then double clicked it to force it into output mode.
Still have Wi-Fi out here.
You know, you gotta do it all again because Kevin wasn't here to record it.
Oh man, come on. That's Kevin. No, I saw it.
Okay. Okay.
I got it.
You got it all. Okay.
Our stream might have dropped, but I recorded it. Can't go this far.
Yeah.
I don't remember if I mentioned it earlier, but one of the characteristics of these projects is the students are trying to include all of the stuff that they've learned over the 4 years. We call these capstone projects, so we sometimes focus them on things like control systems, because we teach that here and we want them to use it. But there are other aspects, power supply design and motor control, and of course mechanical design that they've learned over the years. We want them to use all that stuff in a focused way. And again, I hope you see that characteristic in all of these. The students do a great job of pulling it all together. So I see no other motion. All set? Yep. So we will continue. Alex is going to tell you about his project.
Thank you. My name is Alex Yagi, and before I get into this, I'm just going to preface that I actually don't have a client through just a little fluke. I ended up with this on my own, so my client is everybody. I'm making this, yeah, Kidder wants to steal it, but the idea behind this is to make it open sourced, so all of the code, all of the STL files, it's all going to be posted at the end of this with a how to build guide. But anyway, it is a plastic tensile tester. So, background for the problem. 3D printed materials don't have uniform strength standards, and the way that you can print them can vary drastically depending on the printer or even just the settings within the printer. So 3D printing is a pretty new technology, and a lot of the materials don't have any information on strengths, and the common ones that you can get from 100 different vendors can have slightly different chemical properties that lead to like really big differences in strengths. And again, you can also print with different settings, different speeds, different temperatures, and you get different strength results. So in order to use these materials in engineering, we really need to understand their strengths, but more specifically their weaknesses. So a simple overview of my solution is a tensile tester, as I've said. Tensile testers are used to determine a bunch of different strength specs in the industry. Basically, they measure two things. They measure stress, which is the force required to pull something apart, and they measure strain, or how much it deflects or stretches while it gets pulled apart. So we need to be able to record both of these values in software, and we need to be able to repeat or generate repeatable stress strain curves, as you can kind of see here, to get all of these nice strength values. So my specific solution is to design and manufacture a super simple and inexpensive tensile tester. We need to measure the linear displacement with a resolution of 0.01 millimeters. We want to be able to measure up to 700 pounds of force with 1 gram of resolution. We need to be able to maintain a constant pulling speed throughout the test, so we get a nice smooth curve. And we need to be able to export all of that data to a computer. And there's a little picture of it. It's also right there. Here is the breakdown of the mechanical system. There are 3 subsystems for this. The first is the force application subsystem, which is parts 1, 2, 3, and 4. That is a high torque DC motor with an encoder attached to it. And then that'll go through a 100-to-1 gearbox, which will then spin a drive rod. That will move this bottom jaw down, pulling the specimen apart. The second system is the linear displacement measurement system, or the extensometer. And that is going to be another encoder on a rack and pinion right here, measuring that specimen. And then the final system will be the force measurement system, which will be a load cell in line with the top jaw so that we can measure all of the force through it. So here is the system diagram. We are going to be placing a specimen in the jaws and then pushing a start button on the UI. That will cause the STM32 to send a pulse width to the motor to start it. The motor will then read how fast it's spinning based off of that encoder and feed it back to the STM to maintain the certain speed. And as the motor spins and the jaw moves down, the extensometer, encoder, and the load cell are going to be sending measurements back to the STM32, which then output through TerraTerm to your computer. So, the first of the subsystems, the force application subsystem. This uses a high torque DC motor, as I already said, and a 100-to-1 planetary gearbox to get the torque that we need. The gearbox is attached to a threaded rod that drives a linear sliding table, kind of like you would see on a CNC machine to move it back and forth. The linear sliding table has a jaw attached to it, and then that will move down. The top jaw will be in line with a load cell to measure the full load, and then the table has the sliding table has a range of up to 100 millimeters, which allows for a bunch of different sizes of specimens, because the ISO, which is the organization that makes the specifications for these specimens, they have a bunch of different sizes that we can test. So the force that we're estimating for one of these specimens, we're going to go with a specimen size of 1A. This means it has a cross-sectional area of 4 millimeters by 10 millimeters, or 40 millimeters squared. Assuming that we're using PLA, which is a pretty common plastic, The tensile strength for PLA is between 40 and 60 megapascals. So calculating for force, that's stress times area, we're getting around 2,400 newtons for one of these specimens, and that is about 540 pounds. So our force application system is going to need to supply at least 240 newtons or 540 pounds. And for a safety factor of around 2, we went with around 1,000 pounds, and that'll make more sense when we get to the load cell. So in order to figure out what type of gearbox I wanted, I kind of knew that I wanted 100 to 1 because it made my speeds work out nicely, along with the fact that the table moves 100 millimeters. Like all of my math works out if I got 100 to 1. But I need to know if the gearbox itself could handle the loads that are going to be put on it. So we're going to calculate for this little system here as if it was a jack. In this case, lifting straight up, which is about as hard of a situation as you could throw at it. In reality, it's pulling down, which is a little bit easier. So lifting up 1,000 pounds with this, or 4,448 newtons, we know that the lead screw, or the screw's lead, is 4 millimeters. So one rotation, it will move 4 millimeters up or down. The mean screw diameter, or the average diameter between those threads, is 10.8 millimeters, and the estimated friction is about 0.2. So there's this very handy equation that is made specifically for this type of setup in a lifting setup. If you run those numbers through that equation, you get 7.28 newton meters of torque. And considering that the gearbox I chose has around 40 newton meters of torque, this gives us a safety factor on that gearbox of over 5. So it is way overkill for the application. Oop, that's the wrong way. So the software to run the motor to run that gearbox and the hardware. The motor requires 12 volts to operate, and the motor driver I've chosen to use to regulate the direction and the speed is the M10 or MD10C. So the STM32 is going to control the speed with pulse width, as you've heard a lot about tonight. And the reason we're doing that is to match the ISO strain rate, which is 1 millimeter a minute. Now this is ridiculously slow. Like you can barely see this thing moving. We're gonna do a test in a minute, and it takes 7 to 10 minutes to pull these things apart. So it moves very slow. And the motor speed is going to be calculated from an encoder that is directly attached to the motor. And that is so it's measuring the speed of the motor before it goes through the gearbox, because if we measured it afterward, the error on it would be ridiculous. So the motor control system. The encoder on the motor provides the feedback for the motor speed. And the STM32 relates a pulse width to the linear speed that the jaw is moving at. So we have a pulse width that equals an RPM, and then that RPM equals a linear speed. If our speed is high, we're going to decrease our pulse width, and then if our speed is low, we're going to increase our pulse width. So the math behind this is 1 rotation equals 4 millimeters of linear movement. 25 rotations per minute equals 100 millimeters per minute, which is the entire length of that linear sliding table. And our gearbox is 100 to 1, which very conveniently gives us that desired speed of 1 millimeter a minute. So the actual control system here, we get our reference pulse width coming in, and then we are going to do error detection on that to see how far off of our desired RPM we are. The controller then sends out its pulse width signal to the motor. The motor speed is read by the extensometer, and it goes back and it does this little thing here. If the speed's high, it decreases. If it's low, it increases. So on to the next subsystem, the linear measurement subsystem. This uses a encoder and a rack and pinion to measure linear movement. The rack and pinion translates linear movement into rotational so that the encoder can read it. And the encoder works by transmitting an electrical field to measure rotation with capacitance. So it's not a regular encoder. A lot of them use just a little octocouple, but this one's a lot beefier. It's resistant to oils and dust and whatnot. But the encoder receives a set number of signals or counts per revolution, and it uses quadrature to multiply these by 4. And the way it does that is it has these two transmitters that are slightly offset, and they send an offset signal. They're offset by 90 degrees. And what that does is, as one signal begins, goes up and over and then down, the other one is offset by 90 degrees. So each rise or fall for each of those two signals can be taken out, and you can get 4 points from every 1 point, or one rise and fall of those signals. So that's very useful. So the way this works is the encoder is going to sit on the top gauge arm, and the rack and pinion is going to measure the movement. The rack is going to be fixed to the bottom gauge arm, and the pinion is going to be moving along the top gauge arm. So the two gauge arms are going to be clipped to the specimen and being physically pulled away from each other, and that rack and pinion is going to be moving while that happens, and the encoder is going to pick up that rotation. So during operation, we're going to see a very slow increase in the distance, and then as soon as it fractures or starts to separate, we're going to see a decrease in force and a quick increase in distance, marking the end of the measurement. And then we're going to be calculating our strain as the original length that we're measuring, the change in length that we're measuring divided by the original length. So here's a picture of the extensometer mechanism, because it's a little bit hard to wrap your head around just me explaining it. It's comprised of 6 main parts. They're all 3D printed to try and minimize the weight of this. Basically, the first part is the housing for the encoder, as well as the bottom gauge arm. So the encoder slides right in there, and it has a shaft and pinion that goes through it, so that as that pinion rotates, the encoder picks it up. This is the top gauge arm, along with the rack. So as that rack goes up and down, it will spin that pinion, and then there's a support bracket. And then it also uses a bunch of lead screws to actually grip the specimen, as you can see over on the left there. So the required resolution for our extensometer. Going back to the specimen size of 1A, the gauge length that we're measuring is 50 millimeters, and our goal was 0.01 millimeters, or 10 nanometers. And with that resolution, we can just barely start to measure the yield point along with the ultimate tensile strength and the strain at the break. So that's why I chose that number. But over 50 millimeters, if we look at our resolution calculation, we have 0.01 divided by 50 equals 0.0002. Multiply that by 100, we get 0.02% strain, which is why I say we'll just barely be able to look at the yield point. We'll be able to estimate it, basically. So the encoder. I'm using the AMT102V, just like a couple other groups have. It has 2,048 pulses per cycle. It can be supplied by 3.3 volts. With quadrature, it goes up to 8,192 pulses per cycle. It's super compatible with STM32, which is what I'm using, as well as a bunch of other microcontrollers. My pinion diameter is 23 millimeters. So if we do some quick math on that, we're going to see that the circumference of it is 72 millimeters, which would mean my resolution for this extensometer is 0.008 millimeters, which is just a little bit finer than my goal. Also, that equates to 34 10,000ths of an inch, in case you were wondering. So that's pretty fine. So attaching the 2 encoders that I'm going to be using, one for the motor, one for the extensometer, to my STM32 is real simple. You use the onboard 3.3 volts that the microcontroller supplies, and then the A and B channels for each of the encoders can just go to any pins that you want that are both hooked up to the same timer. So A6 and A7 and A8 and A9 work great. This way I can hook up the STM with this really nifty thing it has where it has this built-in encoder mode on its timers, so it'll automatically increment a counter when it's spun clockwise and decrement it when it's spun counterclockwise. And it will do quadrature and everything for you. So instead of having to do all of that in your code and say, look for this pulse and then multiply it by 4 and do this and blah, 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 it just does it all for you and increments a counter that you can use. So it's way less of a headache. So some of my extensometer code is right here. What you see at the top, those 2 pound defines there, is the encoder counts per revolution and the pinion circumference being defined. The resolution is then calculated as the circumference divided by the counts per revolution. And then we read the counts from the encoder and multiply them by the resolution to get our distance. On the other side, we have the motor encoder. And this defines some target counts per minute. So this is how many counts we want to be seeing in 1 minute. And then it will scan every 10 milliseconds to see if we're getting a live counts per minute. And then it will match the live counts per minute to the target counts. And if it's low, then it tries to speed up. If it's high, then it slows down. That's that control system. Finally, we're on to the force measurement subsystem. This uses a load cell in line with the specimens in the jaw. The force measurement system is pretty basic, so it does have to be zeroed before each test to ensure that it hasn't wandered. And the load cell's rated up to 1,000 pounds, hence that 1,000-pound number from earlier. And everything's tried to be placed as inline as possible to minimize bending error, because that was a problem for a little bit. So how a load cell works. Load cells measure very, very small changes in millivolt ranges. They're typically set up in a Wheatstone bridge configuration, so that as you bend the material, you get that tiny, tiny change in the millivolts. So in order to measure that, we actually need a HX711 amplifier, or any amplifier, but in this case, a HX711. And that HX711 also happens to be an A to D converter, which is really convenient, so we don't have to do as much processing on our STM32 side. So implementing all that, the HX711 amplifier and load cell can both be powered by the 3.3 volts on the STM32. The data in clock can get set up to any pins that you, they don't need to be on a timer basically, just any input-output pins on the STM32. And then you can read the voltages from the load cell and convert them to a force with the STM32 and the HX711. And then it's pretty simple to set up in some code a little calibration with some known weights to give us a conversion from the voltage that we're reading to pounds, or in my case grams, with the STM32. So here is my timeline. The first 4 weeks we were working on getting just an encoder working. I'd never really worked with the AMT 102-V before, so getting that working and then getting getting the math right and getting it to display millimeters. That was the first demo. And then for the second demo, it was getting the linear sliding table to actually crush something, getting a working control system. And then finally, most recently, I've just been working on putting it all together, putting together the force measurement system and the frame, and yeah, now it's all done. So here's the cost to build. The biggest things were the planetary gearbox was pretty expensive, and then the aluminum extrusion and all of the nuts and bolts were definitely the next biggest cost. Everything else was kind of just small things adding up. Here's some pictures. You can see the device holding the specimen and the green extensometer there, along with the linear slotting table. And then the load cell and the planetary gearbox. I'll show you all of this up closer in a second. But I did want to show you this up here because it's this was my first test on some PLA, or not my first test, but one of my first tests on some PLA. It broke at a max mass of 236 pounds. Its ultimate tensile strength was over 2 million pascals, or 26 million pascals, or 26 megapascals. And this was the stress strain curve that I got for it, which I was pretty proud of. I also did it on ABS, which unsurprisingly had a higher breaking point. This was really old ABS, so it kind of didn't move at all and then snapped and then stretched right back to what it wanted to be before. So I would discount this one. This was the one I was really happy about. This was PETG. It had a max mass of 344 pounds, 29 million pascals, and the stress strain curve looks almost exactly like a stress strain curve should. And also the specimen didn't fully break. It just stretched and would just keep stretching and stretching and stretching. It necked down, as you can see. It acted like a metal, and I was really happy about that. So, any questions about the presentation? Okay. So, I'm gonna walk over here if you guys want to come over. So I'll start off by saying, because you can do different size specimens in this, it is not currently outputting the stress and strain directly. It is outputting a distance and a weight applied to the specimen. And then I have been going in Excel and doing all of the conversions myself, but it's pretty simple. Anyway, this is the extensometer. If you want to come up and play with it, you can see that it live in your hand will update. And then I will also calibrate this for you real quick. I absolutely can run it as fast as it goes. So now you can see, yeah. Well, it won't meet the spec, but it should. If this was a perfect machine, it would still make the same chart, but it's not quite. You'll see in a second. It's now outputting weight, as you can see if I push and pull on this a little bit. So we've got our weight, we've got our distance. That's how slow it's supposed to go. So we're not going to do that. I'm going to hold it here, and you're going to watch the millimeters slowly going up, and the grams. I don't know, they should be going up more. I guess they're going up fast enough. This is going to take a while. I'll sit down. You guys are probably going to want to stand over here or behind me to get the best view of it. But this should stretch 7 millimeters. Probably about 5 or 6 before you really see it necking down.
Alex, you said this is 100 times faster? Or?
I actually don't know the math on how much faster this is. This is just max speed for this motor.
So So you expect it to get to 7 or so, you said, millimeters?
Yeah.
Or 2 now?
And we're at 2 millimeters. Oh, that was a lot faster than I thought. Okay,
Broke
so
at the anchor.
this one, I think it was because of the speed. This time it broke at the anchor. And this is one of the problems that I ran into making this, is actually gripping these things is a little difficult, because all the metal ones just have teeth that dig into this end bit, and that's fine. But that doesn't work quite as well with plastic, so this T-slot is what I came up with, and it works pretty well. And while that did break in the wrong spot, usually it's supposed to break in the middle, that does still work. The ABS one did that. I was still able to get a reading with that. But yeah.
So yeah, you would still be able to get like Young's modulus, the steepness of that stress strain curve out of that region that we were testing.
Like I said earlier, if you come look at this one, this was the PET-G at the proper speed. And you can see that this zone right here, we're looking for kind of a straight line right there, and we totally got it. So that was the part that I wasn't sure if we'd get the resolution for, but we can for some
plastics. That's to measure
plastics.
how rigid materials are.
Yeah, and as you can see, PLA, please come up and like bend these and play with them. Like PETG, I can bend and it goes right back. PLA, if I did that, it doesn't want to go back as much, and you can feel that it has more force to get it there.
Did you try to test these as well?
Those
Were you
are
able to-
spacers for my vice. So.
Can you test something like this, or does it have
Which
to be
material
in
do you
this
use in the
actual
lab?
format?
You could do anything that you did with the Tinius Olson with this realistically. So if you wanted to crush surges with this, you could.
Oh, did you bring your crushed piece that you did? In
Feel free to come up and play with it though.
Did you bring your crushed piece from class?
You want to talk about the stretch marks?
Oh yeah, sure. I did have these on my have this on my slide, but I didn't really talk about it. These aren't solid either. So all the calculations I did were for solid materials. These are about 50%. So the 540 pounds that I calculated for PLA, I saw about 236, which makes sense for about 50%.
Yeah. All right.
Anybody have any questions for Alex? So I think this is going to get regular use in our lab. Yeah.
So he didn't.
Professor Kidder does a lot of this stuff, and he's already expressed a very strong interest.
Yeah. And he said he didn't have a real client, but this started because a real client came and asked for a slightly different machine, and another student was going to tackle that one, and Alex decided to go this route. And so there's a need for these machines because PLA is such a new material to work with, and the mechanical engineers need these numbers so they can do their designs right. So.
And similar to the previous projects, if you buy a commercial one of these, it is expensive.
Yep.
Yeah. Even for plastics,
yeah,
$3,000 is the cheapest, and that's for one that can't do specimens this big. They have to be smaller, like 100, 200 pounds max.
And what was the reason for going slowly?
It's the standard.
Oh, okay.
It produces a smoother curve. Like if I were to graph this curve, you'd probably see it like jump a bunch. But yeah.
Well, Alex will be here in a little while. We're running a little late. We'd like to show you the last presentation, and then you can talk to the students. As we're finding the microphone, I just want to say thank you again, everybody, for coming. And the next two students will talk about a project that is intended for the campus here. Amazingly enough, we mentioned Jose Lizardo a few times earlier. He pitched this project too, totally different, but mainly because he wants to grow a mango tree and he wants to grow it in our greenhouse. So we needed a control system to do that. I'll let the two students here explain that.
Hi, I'm Aaliyah,
And I'm Ruby.
and this is our project on modern greenhouse control. Modern greenhouse control is defined by automating systems that read from various sensors, and this reduces the labor needed to maintain plant health. Optimal light is needed from natural sunlight and grow light, and year-round production of flowers, vegetables, and fruits are available. Multiple plant zones provide different plants that grow in the same facility, and they need different needs. Our current greenhouse does not meet these standards. It's controlled by a Wadsworth system, which is outdated, and as you can see here, it's hard to read the menus because of the sunlight, and it's menus within menus, so it's hard to navigate. There's no grow lighting, and there's no full zone control, for example, because of broken equipment. For example, this temperature and humidity sensor doesn't have a humidity sensor reading that's working right now. We were presented with the problem from our client Jose Lizardo to upgrade the existing Wadsworth control system with a modern industrial computer to allow year-round capability, improve the usability, and to improve monitoring of temperature and humidity sensing along with light measurement. And we will be able to expand in the future through additional modules. Since this is only the beginning of the greenhouse swap over for control.
So our solution is to take this. I don't know if you can see my mouse on here. Okay. We have this building in the greenhouse. It's a previous project of a student's. It's been here for ages, and it doesn't get used. And we are going to be recreating the control system. And to do that, we don't want to take everything out of the greenhouse now because we'd kill all the plants. So we're going to implement it on this. And we'll be able to minimize everything that's in the greenhouse now. We can size down and put in here in these little convenient panels on the side. This is just to show you where it is in the greenhouse that we have on campus. Most of you know where it is, but if you're walking down the red brick path to green, it'll be right on your right. And there's two sections. It's going to be in the section closest to the building. This is our diagram of the simulation system. Starting in the center, we have our controller. All inputs come into the controller and all outputs are driven from it. The blue arrows represent the inputs. These include our temperature and humidity sensor, our light sensor, and also simulated outside weather conditions. That lets us recreate real-world environmental changes inside, so without actually having to move the whole system, because as you could see, it was huge and unmovable. The controller processes the information from the inputs and sends it out to the circulation fan, the heater, the exhaust fan, and the side vent to make decisions and maintain temperature and humidity. And then we'll have the user interface, which communicates back and forth between the controller and a user. Let me see. So modern greenhouse control is works on a priority order, and we want to implement that in our system now. So first in the priority is greenhouse safety and manual control. So if we want to take it out of automated control, we can put it in manual. And then below that is environmental conditions. So in normal operation, the controller is consistently comparing the measured temperature to a set point. Or the measured humidity, or the outside conditions. But we want to focus on the center one here. The temperature control controls the heaters, the vents, the circulation, and exhaust fans, and that maintains the scent temperature, and that's the most circulated control we'll be using for this system. This is our overall system block diagram. We wanted to put it like this to make it a little bit easier for people to understand what's going in and what's coming out. So we have the HMI that's going into the PLC, and the PLC has two output add-ons, the analog for precise voltage control and a relay output for simple switching. We have full HMI, we have the HMI connected on the Ethernet port of the click, and this is two-way communication. In dark blue, we have the temperature and humidity sensor. And then in the light blue, we have the stuff it's controlling. In the red, we have the grow light and the par meter. And in the purple, we have the connections.
First, we're going to define a programmable logic controller. It's an industrial computer. This differs from a microcontroller because it's simpler to use and it's for assembly-like situations, which we'll encounter in the greenhouse. It can operate in harsh conditions, which is 32 degrees Fahrenheit to 131 degrees Fahrenheit. We selected the click because it has Ethernet connection, which allows for long-range communication. It interfaces with existing relay-based hardware currently in the greenhouse. It supports the inputs and outputs we need, and it's relatively inexpensive compared to other PLCs. It works by using ladder logic, which we have an example here. So it's making sure that this output stays between 0 and 100. When it's less than 0, it forces it to 0, and if it's more than 100, it forces it to 100. Next, we're going to look specifically at the temperature and humidity sensor system, which is highlighted in yellow. This is the waveforms to communicate to the PLC from the temperature and humidity sensor. We start with a single bus communication, which carries the temperature and humidity on the same line. If it's a 70 microsecond pulse, it's a 1-bit, and if it's 26 to 28 microseconds, it's a 0-bit. This is too fast for the PLC to pick up, so we use a microcontroller. We used our Arduino Leonardo, which had more than one serial output other than the USB. This is a 0 to 5 volt pulse. Next, we converted it with a MAX 485 transceiver chip. This is a RS recommended standard 485 differential signal, which is alternating between A and B, and this can allow us to convert to RS-232 with the isolated network adapter. This is just shifting this signal, and now the PLC can read it. Currently, we have a separate temperature and humidity sensor, and now we have a combined temperature and humidity sensor called the DHT11. Here's some specifications. It's not a fast response time, but this is okay for a greenhouse setting. The purpose of the temperature and humidity sensor is to be a feedback for the circulation fan, exhaust fan, heater, and the vent. The lower and high limits for temperature and humidity are set by the user on the user interface, and you can change between Celsius and Fahrenheit. Some of the key points from my Arduino code is that I set the slave ID to 2, and then I have an enable pin for the MAX 485, which tells the signal when to listen and when to read. There's a matching baud rate of 4,800 bits per second, which matches another device on the line. We have whole numbers to the PLC because it only takes unsigned 16-bit register values. So we have to multiply the values by 10. Lastly, we have a pull function, which is in charge of listening, gathering the information, and then sending it back to the PLC. Here's the ladder logic. On the first rung, we have the PLC calling for the specific slave ID 2. When that's successful, it triggers the next 2 rungs, which just divide the value by 10 because we had to multiply by 10 in the Arduino code.
The next system we're going to focus on are the output systems. They're each kind of simple, so I just want to go through them all together. First, we're going to focus on the venting system. The main purpose here is to bring the outside air to help regulate the internal environment. What makes this different What makes this different from the system that we have now is that it opens proportionally based on the temperature and humidity. So instead of overshooting and opening all the way, we'll make smaller adjustments and keep things stable. In a normal condition where the greenhouse is within range and conditions are reasonable, the vent will sit at about 50% open just to maintain airflow. And then we will allow for manual control through the HMI for this. This slide shows how we actually implemented the vent control. Mechanically, we designed the system to replicate the motion of existing greenhouse vent, which is right here. The shaft will turn and it pushes down, which is kind of hard to see on this picture, but it's shown better here. As this shaft turns, it pushes this arm out. So if this shaft turns 127 degrees, as shown here, then it will open. About 60 degrees, which is our 100% open setting. And here is our ladder control diagram. We're going to run through this same temp high setting for each of these systems. So when the temperature is high, you can see here it does a little bit of math and outputting to the HMI, but this is 100% open when the temperature is very high. For the heating, all we're doing here is going to be simple switching. The heater is going to be on if the temperature is above a set point and off if it's the heater is going to be on if it's below a temp set point and off if it's above one. And you can see here when the temperature is super high, this math here is just a setting that we chose to have the heater off. This can also be put in manual mode. The exhaust fan, the purpose of this is to remove air quickly from the chamber when it gets too hot. So it's a little different. We'll have a circulation fan next, and you'll see the difference there. And this is kind of the same thing as the heater. It's an on-off, but it'll be on when the heat is too high, and then off when it's maintaining or below. And you can see here when the temperature is high, it sets on. That's what set means. It'll say reset if it's turning off. And then this can also be set in manual mode. For the circulation fan, the purpose of this system is to prevent stagnant air and create more uniform conditions throughout the chamber. So unlike the exhaust fan, it won't react to the heat. It's like a support system. During normal operation, the circulation fan stays on to keep air moving. This helps eliminate hot or cold spots and ensures that the sensors are reading more accurate representation of the overall environment. If the system is shut down or if the temperature goes too low, the fan turns off. And this will also be allowed to be controlled in manual mode.
Next, I'll talk about the grow light system, which involves the PAR meter, which is also highlighted in yellow. Here's the system. Oh, goodness. Here's the system where the panel is suspended above a PAR meter, which PAR stands for photosynthetically active radiation. This is the light range from 400 to 700 nanometers, which encourages photosynthesis. The PAR meter measures in ppfd, and that is photosynthetic photon flux density. It's a light intensity measurement within this PAR range. The meter is outputting RS-485 communication and is 1 foot away from the panel. When it's 1 foot away, the range is 0 to 200 micromoles per square meter per second. I use 0 to 10 volt dimming to control the input to the panel. And I also use this LED driver to do the 0 to 10 volt. Some of the user-defined variables on the HMI will be the PPFD output, which the user can set between 0 to 200, the operating hours, and the manual on-off. I chose the proportional control for this system because it's a slow system and it doesn't need to move very fast. It's a robust system and it's less likely to fluctuate depending on disturbances, and allows the user to pick a value between the optimal photosynthetic range. Here's my control loop where the user enters a PPFD set point. It goes to the PLC and it outputs an input voltage to the grow lighting that it thinks that it needs. And we see this through visible light. It's fed through to a PAR light meter. This outputs a measured light output, and it's compared to the set point and feeds back into the PLC as an error. If this measured light output is higher than the set point, it will lower the input voltage to the grow light, and it will raise it if it's lower than the set point. This is the ladder logic. I'm receiving data from slave ID 1, which is the PAR meter. I use a self-adjustable bias, which uses a set point to eliminate recalibration. Then I use the proportional control equation, which is set point minus actual PPFD multiplied by a gain, or KP, which is calculated by max voltage output percentage divided by the max PPFD, and then it's added to the bias calculated above. The last two rungs are just keeping it between 0 to 100%.
So the last system we have to talk about is the HMI. So what is a HMI? It stands for Human Machine Interface. At a basic level, this is the user's way of interacting with the system. It's essentially an industrial touchscreen that's designed to operate in harsher environments like a greenhouse. The main reason we're using an HMI is to make the system more accessible. Instead of needing to go into the PLC program, the user can easily monitor conditions and adjust settings directly from the screen. It also acts as the link between the user and the Click PLC, so you can control and it will display in real time. Communication is handled over Ethernet, which gives us reliable long-range connectivity between HMI and the controller. And the way that this actually works is tag mapping, which is super important with the system that we have set up. So essentially you can set a tag in the PLC and connect it with the HMI, and they'll communicate through that. These are a couple pictures of our HMI menus now. The first one on the left is our home screen setup. This is temporary. We'll have more options than that, but we just wanted to show what it would look like at the end. So here we have two options. You can go to system set or monitor. And system set, you can set specifications, and monitor, you'll be able to see what's happening. Right here, this is our monitor screen. And this is, again, temporary because we are simulating the temperature and humidity set points so we can make sure that everything works correctly. So these ones are settable. But a big thing that I wanted to focus on when we were creating the HMI was making it so you didn't have to switch between every single screen to go back and check and see what the set points were, or see just like what is going on in the system. So I'm trying to implement like easy to see conditions for each screen, so you can like shortcut menus almost, so you can see what's happening and make decisions based on that. These are some photos of our entire system. It looks a lot more full on the diagram photos. So this is our little heater and our lighting. And then here you can see it's upside down, but that is our vent. You just, if you wanted it to be open. It's this small area here. The whole thing isn't the vent, just to be clear. And then this is our wiring and our PLC on the DIN rails. Unfortunately, we can't bring everything over here because it's like 1,000 pounds. This is our timeline. It just shows we spent a lot of time planning out what we were going to do, and then we split up around the middle and worked on our own systems. And now for the last couple weeks, we've been troubleshooting and testing what we have. Our total cost, I'm not going to go through every single thing, but each system, like a PLC and an HMI, are each around $500 to $1,000. So that's quite a lot of money. And then a big thing that we had to spend money on now was cutting aluminum. And aluminum sheets are super expensive. So we do want to point out that this system isn't done, and we're expecting to expand in the future. So this is just for the system that we've put together, and as we implement it further into the greenhouse, the total will change. And before I ask for questions, I just want to let everybody know that we're having a hanging basket plant sale this week, and that's from 11:30 to 1 every day except for Thursday, which is 10 to 5 p.m. So please stop by, get your mother a hanging basket, get your friends hanging baskets. Who doesn't love flowers? We all planted them. We love Plant Club. And those are some pictures, and we've got some on our desk over there. Any questions? I don't have any pictures of that in the slideshow, but basically if those are highlighted, so like see the circulation fan says on and it's highlighted, it'll do the same thing in the ladder logic. It'll highlight each thing if we're connected and it's monitoring. Otherwise, you don't need your computer connected to run this, which is why we chose it. So when it's connected, you can monitor it, but when it's not, this is our only monitoring system. Yes. Right. Right. And so, yeah, that's what we wanted to focus on, was making sure it was easy to use. And then you don't need to be a coding genius to figure out how to troubleshoot the PLC.
Is this a true statement? Do modern greenhouse operators know what the PPFD needs to be for certain plants? Is that the way that's used?
You would set it because like seedlings need a certain amount of PPFD output, and like a full-grown plant might need more or less depending on the plant. Yeah, it's supposed to be at the top of the light plant canopy, so it actually gets an accurate reading, but yes. It adjusts to the sunlight. Yeah.
It's on a cloudy day?
Yes.
St. Dennis, I've worked in a couple of greenhouses, and knowing exactly what type of light certain plants need is actually like really important. Yeah, that's your first statement. Okay. We have charts usually of every plant what they usually like. So knowing that is very important.
And wasn't it, we talked about so many things with the menuing system, but were you imagining implementing, like zone 1 has a certain kind of plant and you would just push a button and the operator wouldn't need to know that?
Yeah, so the point, what I was planning on doing is, which it's not implemented yet, we'll have settings, so like this type of plant, this type of plant, this type of plant, and the user wouldn't necessarily have to know exactly how much light it is. We would just do
They
that.
want tomatoes today.
Right.
Jose wants mango trees.
And it would just be typical plants in the greenhouse we wouldn't have, because we've got like lime trees and other tropical plants. It wouldn't be all of those things. It would just be like more typical Vermont plants.
Okay. So you fix boats and you run greenhouses.
Or you fix both?
Oh, no. I thought it was Kidder saying it's you. Right. What are you going to show us?
We're over here. So unfortunately, the PLC that I brought over doesn't work. So you can, if you want to come over and take a look at the stuff that we're using, you can. Otherwise, we're going to take a walk up to the greenhouse, look at the plants, look at the flowers, and importantly, look at our system. Most importantly.
I believe it's set to 150 right now, but if you were to put your hand over, you can see that the light increases the full brightness because it thinks it's dark. Yeah. I don't know. It could be set through ladder logic right now. It's not uploaded onto HMI yet. Yep. Clip's not responding. So. No, we're gonna take a pause while those vents open because they're awful.
It just sounds like a haunted house.
Oh, okay. Yeah. Imagine being in here late at night.
We want to like put brackets to secure these better. Right now we just have it hold up by tape, and we need to put up the circulation fan, and we're thinking like right about here. And we need to connect the heater still and make this look a little more finished looking. It's a lot right now. Are you wanting to show something else for that? No, I'm set.
The fans?
No, it's okay.
Do you have the exhaust fan associated with it?
Yep, I'm just uploading the program now. Yeah. If everybody wants to kind of squeeze in on this side, I'll be able to show you a couple things. I'm gonna put this down. Watch out. Just the exhaust fan. But the exhaust fans and the HMI will be running. Yeah, actually, this should work. Oh wait, let me just. Let's see if this works. All right, so you can see here, I'll go back. I'll see if anybody wants to see how this works. I can't hit the home button. There we go. So we have these two menus here. We'll be adding to that, but for now, we have system set and monitor. So right now we have the daytime, because it's daytime, the daytime temp range set between 80 and 70. And you can see this is part of the like keeping the menus together or like visible for people to see. The temperature is very high and high. That's because, or the humidity is high. That's because in the monitor section right now, these are, I don't know why it's 171, but we can edit these to make sure that all the systems are working, so we can set everything. So right now the temperature is very high, which means it's over 100 degrees, but we could set it down to 75. and be in range. But now the humidity's too high, so that's why the exhaust fans are still on. But we could put that, I don't remember what that was set for. Let's say 40. I don't remember what that was for. Let's go back. But that's what we'd wanna. Interesting.
I would also just like to mention, I accidentally stuck my finger in the fan. I have decently thick acrylics, and it didn't break. So,
Okay.
I don't know what kind of test that is, but it withstood it.
This is interesting. Not 100% sure why that's not turning off, or why this isn't setting right, but it's like not even changing it. But anyway, we put the temp to 0.
Okay.
The temperature is very low, and the exhaust fans will turn off. You can see here it's lit up low. For some reason the humidity is not setting. I think I changed the one of the numbers. So yeah, that's the key part about all this is that you have to keep everything in line. If you change one singular number, it messes up your entire system. And we've been dealing with that a lot. So we've been transferring systems back and forth. We're finally completely integrated onto one PLC, so we don't have to keep switching. But now it's just getting all those numbers in line, so that's been kind of a mess. But overall, we're pretty confident that this is going to come together well. It's just a matter of getting all the numbers in the right place.
So you guys, we said before, a lot of the groups, you guys do it some more time so we can find a personality.
Yeah. Yeah. If you guys want to take a closer look at our wiring, it's wonderful. You definitely can. And besides that, the vent, unfortunately, is having a hard time today. So it's up there. But if you want to take a look at how it works, we can pull that down too. Oh, wow. Imagine trying to not hit your head on this when it's pitch black in here. It's a great time. Well, we might keep this up so you can see the actual system. But this motor will turn, and it's not tight enough on here to hold it in place right now. But it'll open, and as it opens, it turns this pot, and as it reduces the air, it can get to the exact position it wants to be in. Just a quick system put up. It's exactly like the one that we have in here now. They have separate motor drivers, and I think they do just about the same thing. Yeah.
Leah, why did you choose the RS-4085 system?
Because you can add up to 32 devices on it.
Okay, so that speaks to expandability and
Yes.
keep adding things. The alternative would be to add add-on cards
Yes.
to the PLC, and that gets quite expensive. But adding Modbus stuff is pretty inexpensive.
If you guys want to look at the old system, it's back here. It's pretty cool to look at, actually.
It's running that, yeah.
This is running now. It's running fine. It's just a lot of the systems don't work, or like the fans don't turn on and stuff. But it's pretty interesting to look at. You can't exactly see these menus at all or know what they need to do. And if you open this up, there's no real computer in here. It's just a bunch of microchips that act as a computer because it's so old. So this was put in I think, like the 70s. Yeah, it's been kind of messed around with since. Like there was an expansion at some point because it was just this section, and now that second zone was added on, and I think they expanded this. But you can look at the pictures from the 80s. There's like old pictures uploaded on the library website, and this is still here. So, which is pretty cool. It's still working. I don't think there's been a lot of upkeep because we contacted the Wadsworth people, and they were like, we don't have record of actually putting anything in here. They were like, it must have been before we had electronic records. So that was super helpful. But feel free to look through the greenhouse. The Plant Club spends a lot of time in here, and they do a lot of good work. And we are excited to be a part of the process of putting this thing back together.
Do you want to explain the actual components of your
The board that you have together.
What board?
You mean the circuitry?
The yeah,
Oh,
well the PLC and the
Separate red ones.
Oh yeah. I'll let Aaliyah kind of lean into that because a lot of those are.
what are they doing?
Okay, so this one's mine, and this is for.
Let me turn the power off so you're not just sticking your hand in the.
Oh, sure. Okay, let's start with this one. This one is for RS485. This is the bus. I don't actually need 3 modules. I can do it with one because I don't need like a new master or they're all the same baud rate. This is for the temperature sensor in here. I used Arduino Leonardo. And let's see what else we can talk about. This is Ruby system that controls the vent. All of this. And right here is the Modbus on port 2. Ethernet is for us to connect to it and program it. This should be
that should be your light.
Yeah, the power meter. Oh, the light. Yeah, this is the light. The 0 to 10 volt adjustable.
That orange one down there is the vent, and then I don't know what the.
This is just power.
Oh yeah, that's just
so,
power.
yeah, that's about it.
It looks more complicated than it's actually. Because there is a lot that goes into the wiring, and then the output is underwhelming.
That's true.
Spent hours doing this.
Remember learning about that guy. This is